Universe, a perpetually expanding amalgamation of galaxies, stars, planets, and myriad forms of matter and energy, presents a profound mystery that has captivated humanity for centuries. Central to modern cosmology is the understanding that the universe began approximately 8 billion years ago with the Big Bang, a colossal explosion that marked the inception of everything we know. This event set in motion the expansion of space, creating the cosmic web we observe today. Scientists have unraveled much about the universe's composition, revealing that ordinary matter, the substance making up stars, planets, and us, constitutes a mere 5% of the universe's total mass and energy. The remaining 95% comprises dark matter and dark energy, invisible forces that govern the universe's structure and expansion, yet elude direct detection. The universe's vastness is almost beyond comprehension, stretching over billions of light-years across. This immensity houses an estimated 2 trillion galaxies, each a collection of billions of stars and untold planets, offering a humbling perspective on our place in the cosmos. The laws of physics, consistent throughout the universe, govern the motion of galaxies, the life cycle of stars, and the intricate dance of particles at the quantum level. These laws have allowed scientists to predict cosmic phenomena with astonishing accuracy, from the paths of planets to the behavior of black holes, those enigmatic entities whose gravitational pull is so strong that not even light can escape. In this cosmic journey, the role of dark energy in accelerating the universe's expansion poses a tantalizing puzzle. Discovered through observations of distant supernovae, dark energy works against the gravitational pull of matter, driving galaxies apart at an accelerating rate. This discovery has profound implications for the universe's fate, suggesting a future in which galaxies drift ever farther apart, leading to a cold, dilute cosmos. The Big Bang Theory. The Big Bang Theory stands as a cornerstone of modern cosmology, offering a compelling explanation for the origin and evolution of the universe. It posits that the universe began as an extremely hot and dense point approximately 8 billion years ago and has been expanding ever since. This theory is supported by a wealth of scientific evidence, including the observation of the cosmic microwave background radiation, a faint glow left over from the early universe, which provides a snapshot of the cosmos just 380,000 years after the Big Bang. This radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, has a uniform temperature throughout the universe, confirming predictions of the Big Bang Theory and offering concrete evidence of the universe's hot, dense origin. Another pillar supporting the Big Bang Theory is the observation of the redshift of galaxies, indicating that they are moving away from us and, by implication, from each other. This discovery, made by Edwin Hubble in the 1920s, revealed that the universe is not static but expanding. The farther away a galaxy is, the faster it appears to be moving away from us, a relationship now known as Hubble's law. This expansion is a key prediction of the Big Bang Theory and suggests that the universe was once much smaller, hotter, and denser than it is today. Moreover, the theory elegantly explains the relative abundances of light elements, such as hydrogen, helium, and lithium observed in the universe. According to Big Bang nucleosynthesis, these elements were formed in the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to combine into nuclei. The predicted abundances of these elements closely match observations, lending further credence to the Big Bang Theory. Despite its widespread acceptance, the Big Bang Theory also raises profound questions and puzzles. For instance, it does not explain what preceded the Big Bang or what lies outside the observable universe. It also introduces the concept of cosmic inflation, a rapid expansion of the universe that occurred fractions of a second after the Big Bang to solve the horizon and flatness problems. This inflationary period predicts that the universe should appear flat and uniform on large scales, which is consistent with observations of the cosmic microwave background radiation. Our early universe. Following the Big Bang, the universe embarked on a monumental journey of expansion, transforming from an infinitesimally small point to the vast cosmos we observe today. This expansion can be likened to a balloon being inflated, where galaxies move away from each other as the space between them grows. In the earliest moments, the universe was a hot, dense soup of particles and radiation, too energetic and chaotic for atoms to form. As it expanded, this primordial fireball cooled, allowing quarks to combine into protons and neutrons, which then formed the simplest nuclei, predominantly hydrogen and helium, through the process of nucleosynthesis. This phase of rapid expansion, occurring less than a trillionth of a second after the Big Bang, is theorized to have been driven by cosmic inflation. Cosmic inflation posits that the universe expanded at a rate much faster than the speed of light during this brief period. This exponential expansion smoothed out the distribution of energy and matter across the cosmos, laying the groundwork for the uniformity we observe in the cosmic microwave background radiation. It is a concept that challenges our everyday understanding of physics, suggesting that the rules of the cosmic scale can differ vastly from those governing our observable world. As the universe continued to expand and cool, gravity began to sculpt the distribution of matter, pulling particles together to form the first stars and galaxies. These celestial bodies acted as cosmic furnaces, forging heavier elements in their cores and releasing them into space when they died, seeding the cosmos with the building blocks for planets and life. The universe's expansion is not uniform, it is influenced by the distribution of matter and energy, leading to the formation of a web-like structure of galaxies and galaxy clusters interspersed with vast voids. This expansion is still ongoing, with galaxies moving away from us in all directions. The discovery that this expansion is accelerating was a groundbreaking revelation, hinting at the presence of dark energy, a mysterious force that permeates space and exerts a repulsive force, counteracting gravity. The exact nature of dark energy remains one of the most pressing mysteries in cosmology, with researchers striving to understand how it will influence the future evolution of the universe. Formation of atoms and molecules. Delving deeper into the mysteries of the universe, we pivot our attention towards the formation of the very first atoms, a seminal event that marked a turning point in the cosmic narrative. This process, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. The temperatures were so extreme that atoms could not form without being immediately torn apart by the rampant energy. As the universe expanded, it cooled down, allowing for the first atoms to emerge. Hydrogen, the simplest and most abundant element in the universe, was the first to form. This element, consisting of just one proton and one electron, marked the dawn of a new era in cosmic history. Helium atoms, slightly more complex with 2 protons, 2 neutrons, and 2 electrons, followed shortly after. These elements laid the foundation for the chemical diversity we observe in the universe today. The formation of these first atoms was a turning point that significantly altered the universe's structure and future evolution. With atoms now stable, they began to gravitate towards each other, slowly building the first stars and galaxies. This era set the stage for the complex chemical processes that would eventually lead to the formation of planets and life itself. Following the monumental formation of the first atoms in the universe, an equally remarkable phenomenon unfolded: the birth of the first molecules. This transition from solitary atoms to the earliest molecules marks a significant chapter in cosmic history, laying the groundwork for the complex chemistry that underpins the universe as we know it. The story of how the first molecules came into existence is not only a testament to the intricacies of the cosmos, but also to the relentless pursuit of knowledge that drives our understanding of it. As the universe continued to expand and cool, conditions gradually became favorable for these freshly formed atoms, primarily hydrogen and helium, to interact in novel ways. Hydrogen, with its single electron, was particularly predisposed to forming bonds with other hydrogen atoms. The emergence of molecular hydrogen, or H2, was a critical step forward. This molecule, though simple in structure, played a pivotal role in the universe's early chemistry. The formation of molecular hydrogen provided the first building blocks for more complex chemical reactions. It acted as a coolant, allowing gas clouds to collapse more efficiently under gravity, which in turn led to the formation of the first stars. These nascent stars were the crucibles in which the first heavy elements were forged, elements that would eventually give rise to the rich chemical tapestry that makes up planets, asteroids, comets, and all living organisms. The exact timing of the first molecule's formation is a subject of ongoing research, but it is believed to have occurred a few 100,000 years after the Big Bang, following closely on the heels of atomic formation. This era set the stage for the intricate interplay of forces that would eventually lead to the universe's structure, from galaxies to planets, and the very essence of life itself. As we trace the cosmic lineage back to its origins, the roles of helium and hydrogen emerge as foundational to the early universe's evolution. These two elements, the simplest and most abundant in the cosmos, were instrumental in shaping the universe from its nascent stages. Their significance cannot be overstated, as they were the primary constituents of the primordial universe, setting the stage for all subsequent astronomical phenomena and the complex chemistry that characterizes the cosmos today. In the aftermath of the Big Bang, the universe was predominantly filled with hydrogen and helium. Hydrogen, being the lightest element with just one proton and one electron, formed the bulk of the matter in the early universe. Helium, slightly heavier with 2 protons and 2 electrons, was the second most abundant element. These elements were crucial for several reasons. First, their simplicity made them the building blocks for all other elements and molecules that would later emerge through nuclear processes within stars. The significance of hydrogen extends beyond its abundance. It played a central role in the formation of the first stars, known as Population 3 stars. These stars were massive, hot, and short-lived, but they were critical for the synthesis of heavier elements through nuclear fusion. As these first stars ended their lives in spectacular supernovae, they seeded the cosmos with heavier elements, which would eventually give rise to new stars, planets, and, ultimately, life as we know it. Helium's role, while less directly involved in chemical complexity, was no less important. Its presence influenced the dynamics of stellar evolution. Stars fuse hydrogen into helium in their cores, a process that releases vast amounts of energy and light. As stars age, they begin to fuse helium into heavier elements, leading to different types of stellar outcomes and contributing to the diversity of astronomical objects we observe today. Moreover, the ratio of hydrogen to helium in the universe provides critical insights into the conditions of the early universe and supports the Big Bang theory. Observations of this primordial helium abundance, along with the cosmic microwave background radiation, offer compelling evidence of the universe's hot, dense beginnings. Cosmic microwave background radiation building. On our journey through the cosmos, where we've uncovered the roles of helium and hydrogen, we arrive at another cornerstone of cosmology, the cosmic microwave background CMB radiation. This phenomenon is essentially the afterglow of the Big Bang, the ancient light that bathes the universe, providing us with a snapshot of the infant cosmos. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB radiation is a pivotal piece of evidence for the Big Bang theory, offering a window back in time to when the universe was just about 380,000 years old. At this juncture in cosmic history, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms, a process known as recombination. Prior to this, the universe was a plasma of charged particles and photons, light particles, which scattered off each other frequently. However, as the universe expanded and cooled, photons could travel freely without being scattered, leading to the universe becoming transparent. The CMB is the relic of this transition, stretched to microwave wavelengths by the expansion of the universe over billions of years. The significance of the CMB radiation lies not only in its confirmation of the Big Bang theory, but also in the detailed information it provides about the early universe's conditions. The tiny temperature fluctuations within the CMB are particularly revealing. These minute differences in density and temperature are thought to be the seeds from which all the current structures in the universe, such as galaxies and clusters of galaxies, have grown. Measurements of the CMB radiation have led to precise determinations of various fundamental parameters of the universe, including its age, composition, and the rate of its expansion. For instance, the CMB data suggests that the universe is approximately 8 billion years old and composed of about 5 ordinary matter, 25 dark matter, and 70 dark energy. The CMB radiation underpins the Big Bang theory, a pivotal concept in cosmology. The Big Bang theory proposes that the universe originated from an extremely hot and dense state and has been expanding ever since. The CMB radiation is a critical piece of evidence supporting this theory, offering tangible insights into the universe's early moments. The discovery of the CMB radiation in the mid-20th century was a landmark event that provided the first direct observational evidence of the universe's hot, dense beginnings. The CMB's uniformity, with its temperature incredibly uniform across the sky at about 7 Kelvin 270, 45 degrees Celsius, yet punctuated by tiny fluctuations, paints a picture of the early universe's state. These tiny temperature variations are crucial. They indicate regions of slightly different densities, representing the seeds of all current cosmic structures, from galaxies to clusters of galaxies. The Big Bang theory predicts that after the initial explosion, the universe was in a state of extreme heat and density, filled with a primordial soup of particles and radiation. As the universe expanded, it cooled, leading to the formation of neutral atoms, which allowed photons to travel freely. The CMB radiation is the relic of this epoch, stretched to microwave wavelengths by the universe's expansion, and observed today as the cosmic afterglow of that monumental event. Furthermore, the detailed analysis of the CMB's temperature fluctuations through experiments like the COBE Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and Planck satellite missions has provided precise measurements of the universe's age, composition, and rate of expansion. These observations match remarkably well with predictions from the Big Bang theory, reinforcing its validity. For instance, the slight anisotropies irregularities in the CMB reveal the distribution of matter and energy in the early universe, which, according to the Big Bang theory, should be relatively uniform, but with minor variations that led to the formation of galaxies and larger structures. The CMB's existence and its properties are thus in strong agreement with the theoretical predictions of the Big Bang, providing compelling evidence that our universe did indeed begin from a hot, dense state and has been expanding over time. Delving into the cosmic microwave background. CMB radiation has opened up new vistas in our understanding of the universe. This relic radiation, a faint cosmic afterglow from the Big Bang, serves as a cosmic treasure trove, revealing details about the universe's infancy and its subsequent evolution. By studying the CMB, scientists have gleaned invaluable insights that have significantly advanced our comprehension of cosmology. One of the most profound learnings from the CMB is the confirmation of the universe's age. Precise measurements of the CMB's fluctuations have enabled scientists to estimate that the universe is approximately 8 billion years old. This provides a concrete timeline for the universe's history, from its fiery origins to the present day, grounding our understanding of cosmic evolution in empirical evidence. The composition of the universe is another area where the CMB has provided critical information. Analysis of the CMB data has helped scientists determine the universe's makeup roughly 5 ordinary matter, the matter that makes up stars, planets, and living beings, 25 dark matter, a mysterious substance that exerts gravitational pull but does not emit light, and 70 dark energy, a mysterious force that is causing the universe's expansion to accelerate. These proportions have profound implications for our understanding of the universe, highlighting the dominance of dark matter and dark energy in cosmic dynamics. Furthermore, the CMB has shed light on the geometry of the universe. The size and distribution of the temperature fluctuations within the CMB suggest that the universe is flat with a margin of error. This flatness implies that the geometry of the universe is such that parallel lines will never converge or diverge, influencing the universe's overall shape and expansion. The study of the CMB has also contributed to our understanding of the inflationary theory, which posits that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The uniformity and structure of the CMB across the vast expanse of the sky support the idea that the universe expanded exponentially during its earliest moments, smoothing out any initial irregularities and leading to the uniform universe we observe today, albeit with slight variations that gave rise to galaxies and other structures. Moreover, the CMB has acted as a backdrop for exploring the potential for new physics beyond the Standard Model. Anomalies and unexplained aspects of the CMB, such as the cold spot or slight discrepancies in temperature fluctuations, invite ongoing research and theories that may extend our current understanding of physics. The Dark Ages and structure formation. As the afterglow of the Big Bang began to fade, the universe entered a period known as the Cosmic Dark Ages, a time that lasted for about 380,000 years to a billion years after the universe's inception. During this era, the universe was filled with a dense, cooling fog of hydrogen gas, rendering it opaque and, in a sense, invisible to the kind of light we can now observe with telescopes. Without stars or galaxies to illuminate it, this epoch stands as an enigmatic chapter in cosmic history, a stretch of time when the cosmos was eerily silent and dark. The Cosmic Dark Ages are a critical period in the universe's evolution, laying the groundwork for the formation of the first stars and galaxies. As the universe expanded, the primordial gas that filled it began to clump together under the influence of gravity. These regions of higher density eventually became the nurseries for the first stars, known as Population 3 stars. Unlike the stars we see today, these celestial bodies were massive, luminous, and short-lived, composed almost entirely of hydrogen and helium. The nuclear reactions within these stars eventually reionized the surrounding hydrogen gas, piercing the opaque veil of the Cosmic Dark Ages and bringing the universe into a new era of transparency and light. This transition, known as cosmic reionization, marked the end of the Cosmic Dark Ages and set the stage for the rich tapestry of structures we observe in the universe today. The light from these first stars and galaxies began to travel through the cosmos, gradually illuminating the once dark universe. This period is of intense interest to astronomers and cosmologists, as it holds clues to the formation of the first cosmic structures and the nature of dark matter, a mysterious substance that exerts a gravitational pull yet does not emit, absorb, or reflect light. Studying the Cosmic Dark Ages poses significant challenges, as the light from this period is exceedingly faint and difficult to detect. However, with advancements in technology and the advent of next-generation telescopes, scientists are beginning to pierce this veil. Observations of distant quasars and galaxies, along with the cosmic microwave background radiation, a relic from the Big Bang, provide valuable insights into this pivotal era. These studies not only shed light on the Dark Ages themselves, but also help us understand the fundamental processes that have shaped the universe from its earliest moments to the present day. Emerging from the Cosmic Dark Ages, the universe embarked on a transformative journey, culminating in the birth of the first stars and galaxies. This pivotal epoch, occurring roughly around 100 million years after the Big Bang, signifies a monumental shift in the cosmic narrative. Initially, the universe was a homogeneous soup of hydrogen and helium gas. However, subtle fluctuations in density, possibly amplified by the mysterious dark matter that pervades the cosmos, began to create pockets where the gas was slightly more concentrated. Gravity, the architect of cosmic evolution, took hold within these denser regions, pulling the gas inward. As these clouds of gas grew denser and hotter, they reached a critical threshold, igniting the nuclear fusion processes at their cores. This marked the birth of the first stars, colossal and bright, primarily composed of hydrogen and helium. These Population 3 stars were giants compared to their modern counterparts, burning with such intensity that their lifespans were relatively brief on a cosmic scale. The ignition of the first stars introduced light back into the universe, ending the Cosmic Dark Ages. These stars were not solitary beacons. They began to clump together under gravity's relentless pull, forming the nuclei of the first galaxies. These early galaxies were smaller and less structured than the ones we see today. Yet they were the seeds from which the grand spirals and vast ellipticals of the current universe would grow. As these first stars aged, they played a crucial role in the chemical enrichment of the cosmos. The nuclear fusion processes at their hearts forged heavier elements like carbon, oxygen, and iron, elements that had not existed before. When these stars reached the end of their lives, they expelled these heavier elements into space through supernova explosions, seeding the cosmos with the building blocks necessary for future generations of stars, planets, and eventually, life. The formation of the first stars and galaxies set in motion a complex web of interactions that would shape the universe's evolution. The radiation from the first stars helped to ionize the surrounding medium, clearing the fog of the early universe and making it transparent to light. This process, known as cosmic reionization, was a gradual one, stretching from about 150 million to a billion years after the Big Bang, and was essential for the universe to become the starlit expanse we observe today. As the first stars and galaxies began to illuminate the cosmos, an invisible scaffold was already in place, guiding their formation and distribution across the universe. This unseen framework is known as dark matter, a term that encompasses a vast portion of the universe's total mass. Unlike the stars, planets, and gas clouds that emit or reflect light, dark matter does not interact with electromagnetic forces, making it completely invisible to our current observational instruments. Despite its elusive nature, dark matter plays a crucial role in the cosmos, especially in the formation of large-scale structures like galaxies and galaxy clusters. The existence of dark matter was first inferred from the gravitational effects it has on visible matter. For instance, galaxies spin at such speeds that, without the presence of a significant amount of unseen mass, they would simply fly apart. Furthermore, the way galaxies cluster together, along with observations of the cosmic microwave background radiation, the afterglow of the Big Bang suggests that there is far more matter in the universe than we can directly observe. Studies estimate that dark matter constitutes about 85% of the total matter in the universe, a figure that underscores its importance in cosmic evolution. Dark matter played a pivotal role in the formation of cosmic structures. In the early universe, slight density fluctuations became the seeds for the first structures to form. Dark matter, unaffected by anything but gravity, began to clump together in these denser regions, forming vast halos that would serve as gravitational wells, pulling in the normal or baryonic matter. This process accelerated the formation of stars and galaxies as hydrogen and helium gas fell into the gravitational pits carved out by dark matter. These dark matter halos provided the necessary gravitational framework for the gas to cool and condense into stars. As these stars formed and grouped into the first galaxies, they followed the underlying dark matter distribution, leading to the large-scale structure of the universe we see today, with galaxies and galaxy clusters woven into a cosmic web of filaments and voids. This structure, predicted by simulations that include dark matter, matches observations of the universe at large scales remarkably well. The role of dark matter in cosmic structure formation is a topic of ongoing research and fascination in cosmology. Its presence is inferred from its gravitational effects, yet its true nature remains one of the biggest mysteries in science. Various candidates have been proposed for what dark matter might be, ranging from exotic particles like WIMPs, weakly interacting massive particles, to axions, particles much lighter than electrons. Despite extensive searches, direct detection of dark matter particles has yet to be achieved, making its study a frontier of both theoretical and experimental physics. Formation of stars. Following the threads woven by dark matter in the cosmic tapestry, we find that the formation of stars from cosmic gas is a natural progression in the story of the universe. Stars begin their lives within vast cold clouds of gas and dust, known as molecular clouds or nebulae. These clouds are mostly composed of hydrogen with a sprinkling of helium and trace amounts of heavier elements. Within these nebulae, regions of higher density can form, often triggered by the gravitational influence of dark matter as well as by the effects of nearby supernova explosions or the collision of gas clouds. When these denser regions reach a critical mass, gravity begins to overpower the internal pressures resisting collapse. The cloud starts to contract, and as it does, the material at the center of the cloud becomes increasingly dense and hot. This process can take millions of years, but it's the crucial first step towards star formation. During this phase, the collapsing material forms what is known as a protostar, a hot core that is the precursor to a star. As the protostar continues to accumulate mass from its surrounding cloud, its temperature rises. When the core's temperature reaches about 10 million degrees Celsius, nuclear fusion ignites. This process involves hydrogen nuclei fusing to form helium, releasing a tremendous amount of energy in the process. This energy generation marks the birth of a new star. The onset of nuclear fusion halts the gravitational collapse, establishing a stable balance between the inward pull of gravity and the outward push of the energy produced by fusion. This delicate balance is what sustains a star throughout most of its life. The size and mass of the resulting star depend on how much material from the surrounding cloud it can gather before nuclear fusion begins. More massive stars form from denser or more extensive clouds and have shorter lifespans because they burn through their nuclear fuel more quickly. In contrast, smaller stars like our Sun have longer lifespans, burning their fuel more slowly and steadily. Stars do not form in isolation. Within a single molecular cloud, many stars can form simultaneously, creating a cluster of newborn stars. This communal birth often results in stellar associations and open clusters, where stars remain gravitationally bound to each other for some time before dispersing. The process of star formation from cosmic gas is not only a testament to the dynamic nature of the universe, but also to the interconnectedness of all cosmic phenomena. Each star's birth contributes to the chemical richness of the cosmos, seeding the universe with elements critical for the formation of planets and potentially life itself. The life cycle of a star is a fascinating journey that spans millions to billions of years, showcasing the dynamic processes that drive the evolution of the cosmos. This cycle begins in the dense, cold cores of molecular clouds, where stars are born from collapsing pockets of gas and dust. As we've seen, the gravitational pull within these regions leads to the formation of protostars, which eventually ignite into full-fledged stars once nuclear fusion starts in their cores. The path a star takes through its lifetime depends largely on its initial mass. Smaller stars, like our Sun, enter what is known as the main sequence phase after their birth. During this stage, which constitutes the majority of a star's life, hydrogen fusion occurs in the core, producing helium and releasing energy that supports the star against gravitational collapse. For a star like the Sun, the main sequence phase can last about 10 billion years. As stars exhaust their hydrogen fuel, their lives continue to evolve dramatically. In the case of a Sun-like star, once the hydrogen in the core is depleted, fusion ceases, and the core begins to contract under gravity. This contraction heats up the core, allowing hydrogen fusion to occur in a shell surrounding the helium-rich core. The increased energy output causes the star's outer layers to expand and cool, leading it to become a red giant. During the red giant phase, the star can engulf planets that are in close orbit, dramatically altering its solar system. The final stages of a star's life are determined by its mass. For stars with masses up to about 8 times that of the Sun, the core will eventually shed its outer layers, creating a beautiful glowing gas shell known as a planetary nebula. The remaining core becomes a white dwarf, a dense, hot remnant about the size of Earth, which will gradually cool and fade over billions of years. More massive stars, however, meet a more violent end. After burning through different layers of elements, their cores eventually collapse, leading to a supernova explosion. This catastrophic event can outshine entire galaxies for a short time and is responsible for producing and dispersing many of the heavy elements found throughout the universe. What remains after a supernova can be a neutron star, an incredibly dense object only a few kilometers in diameter, or if the star was massive enough, a black hole, a point in space with gravity so strong that not even light can escape. The life cycle of a star is not just a sequence of events, it is a cornerstone of cosmic evolution, contributing to the chemical complexity of the universe and influencing the formation and evolution of galaxies. Within the crucibles of stars, a process unfolds that has puzzled and fascinated scientists for generations: the creation of heavier elements from lighter ones. This alchemical process, known as nucleosynthesis, is the heart of a star's contribution to the cosmos. It begins with the fusion of hydrogen, the most abundant element in the universe, into helium, the second lightest element. This process releases energy, which provides the light and heat we associate with stars, including our Sun. But the story doesn't end there. As stars evolve, particularly those more massive than the Sun, their internal conditions become extreme enough to fuse helium and other lighter elements into heavier ones. In the cores of these stars, temperatures and pressures reach staggering levels, enabling a series of nuclear fusion reactions that form elements such as carbon, oxygen, silicon, and iron. Each step up the ladder of complexity requires increasingly harsh conditions, only found in the cores of the largest stars or in the explosive environments of supernovae. For instance, carbon is formed from the fusion of 3 helium nuclei, a process requiring temperatures exceeding 100 million degrees Celsius. The journey from lighter to heavier elements culminates with iron, the most stable of all nuclear matter. Here, the process of fusion reaches a critical threshold. Unlike lighter elements, fusing iron does not release energy, it consumes it. Thus, when a star's core is converted to iron, it marks the beginning of the end of the star's life. Without the energy release from fusion to counteract gravity, the core collapses, leading to a supernova explosion for the most massive stars. It is in the cataclysmic violence of these supernovae that the heaviest elements of all, such as gold, uranium, and plutonium, are created. The remnants of these explosions, enriched with a cornucopia of elements, are then cast into the cosmos, seeding future generations of stars and planets. This cosmic recycling process ensures that the elements necessary for life are not confined to the interiors of distant stars, but are instead spread throughout the universe. The iron in our blood, the calcium in our bones, and the oxygen we breathe are all forged in the fiery hearts of stars long gone, a testament to the profound connection between the cosmos and every living thing within it. When stars reach the end of their lives, the universe stages a dramatic farewell, showcasing a variety of cosmic phenomena that depend on the mass of the dying star. The death of a star marks not just an end, but also the beginning of a new chapter in the cosmic cycle of matter. For stars like our Sun, the final act begins when all the hydrogen in the core has been fused into helium and the star expands into a red giant. This expansion is the star's attempt to find a new equilibrium as it starts fusing helium into heavier elements like carbon and oxygen in its core or in shells around the core. Eventually, the star sheds its outer layers into space, creating a visually stunning planetary nebula, leaving behind a hot core that cools and dims over time, becoming a white dwarf. This dense, Earth-sized remnant will spend billions of years cooling and fading into the cosmic backdrop, its nuclear fires extinguished. The fate of more massive stars is far more violent and spectacular. When these stars exhaust their nuclear fuel, they undergo a series of increasingly rapid and energetic fusion reactions, creating a layered structure of elements with iron at the core. Since iron cannot produce energy through fusion, the star no longer has a source of pressure to counteract gravity, leading to a catastrophic collapse of the core in a matter of seconds. This collapse triggers a supernova explosion, one of the most energetic events in the universe, briefly outshining entire galaxies and dispersing the elements forged within the star into space. The remnants of this explosion can lead to the formation of either a neutron star, an incredibly dense object only about 20 kilometers in diameter, but with more mass than the Sun, or, if the star was massive enough, a black hole, a point in space where gravity is so strong that not even light can escape. These end-of-life events are not just spectacular cosmic fireworks, they play a crucial role in the evolution of the universe. The elements produced and dispersed by dying stars seed the cosmos with the materials necessary for new stars, planets, and potentially life itself to form. Supernovae, in particular, are responsible for creating and distributing the heavy elements essential to our existence, such as iron, calcium, and carbon across the galaxy. Formation of galaxies. Delving into the cosmic ballet of galaxy formation, we embark on a journey that spans billions of years, where the universe's fundamental forces choreograph the creation of these colossal celestial entities. Galaxies, vast islands of stars, gas, dust, and dark matter are the building blocks of the cosmos, and their formation is a tale of both simplicity and complexity, woven by the laws of physics. In the beginning, following the Big Bang, the universe was a hot, dense sea of particles. As it expanded, temperatures dropped, allowing protons and electrons to combine and form neutral hydrogen atoms. This era, known as recombination, marked the universe's transition from opacity to transparency, allowing light to travel freely for the first time. However, the universe was not perfectly uniform. Slight density variations, or ripples in the fabric of space-time left by the Big Bang, set the stage for galaxy formation. Gravity, the architect of the cosmos, took center stage, amplifying these tiny fluctuations. Regions slightly denser than their surroundings began to attract more and more matter, growing increasingly more massive. This process is beautifully illustrated by the concept of gravitational collapse, where gas clouds, primarily hydrogen, begin to collapse under their own gravity. As these clouds condensed, they formed the first stars and protogalaxies, simple structures that would evolve into the complex galaxies we observe today. However, galaxy formation is not solely a product of gravity's inward pull. Other forces played pivotal roles, such as dark matter, a mysterious substance that does not emit, absorb, or reflect light, but exerts gravitational effects on visible matter. Dark matter makes up about 85% of the universe's total matter content and acted as scaffolding for galaxy formation. It clumped together in the early universe, creating gravitational wells into which ordinary matter could fall, accelerating the process of galaxy assembly. Moreover, feedback processes, where energy from star formation and supernova explosions heated and expelled gas from early galaxies, also significantly influenced their evolution. These energetic outflows prevented the gas from cooling and collapsing too quickly, regulating the pace of star formation and leading to the diverse array of galaxy sizes and shapes observed today, from spiral galaxies like our Milky Way to elliptical and irregular galaxies. As galaxies grew, they did not evolve in isolation. Collisions and mergers between galaxies were common, especially in the crowded environment of the early universe. These cosmic encounters could dramatically alter a galaxy's structure and star formation rate, creating new morphological features, such as spiral arms, and seeding the growth of supermassive black holes at their centers. Today, galaxies continue to evolve, influenced by their interactions with their environment, including other galaxies and intergalactic gas. The study of galaxy formation and evolution not only sheds light on the history of the universe, but also provides crucial insights into the fundamental processes governing the cosmos. It is a narrative of creation, transformation, and interaction, highlighting the intricate dance of matter and energy that shapes our universe. In the vast expanse of the universe, galaxies are the grand assemblies of stars, gas, dust, and dark matter, presenting themselves in a variety of magnificent forms. These cosmic entities, numbering in the billions, are classified into several main types, each with its own unique characteristics and origins, painting a rich tapestry of the cosmos' diversity. Among these types, spiral, elliptical, and irregular galaxies stand out, each telling a different story of cosmic evolution and interaction. Spiral galaxies, such as our Milky Way, are distinguished by their flat, disc-like appearance, featuring swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars around which the arms, sites of active star formation, wrap themselves in graceful arcs. These arms are rich in gas and dust, the raw materials for new stars, and are often highlighted by bright nebulae and young, hot stars that give them a distinct glow. The spiral pattern is thought to be a result of density waves that sweep through the galaxy, compressing gas and dust to spark star formation in a ripple effect. Elliptical galaxies, in contrast, lack the defined structure and spiral arms of their disc-shaped counterparts. They range from nearly spherical to elongated shapes and are composed mostly of older, redder stars with minimal gas and dust. This makes them relatively barren in terms of new star formation. The size of elliptical galaxies can vary widely, from giants that dominate their local clusters of galaxies to dwarfs that flit like shadows around their larger neighbors. The formation of these galaxies is often attributed to the merging of smaller galaxies, a process that strips away gas and leaves behind a smoother, less structured formation. Irregular galaxies, as the name suggests, lack the coherent structure seen in spiral and elliptical galaxies. These galaxies are often chaotic in appearance, without a defined form, and are rich in gas and dust, making them fertile grounds for star formation. Their irregular shapes can be the result of gravitational interactions or collisions with other galaxies, which distort their structure and trigger bursts of star formation. These galaxies are important to astronomers, as they often provide insights into the processes of galaxy interaction and evolution. Beyond these broad categories, there are also subtypes and peculiar galaxies that defy easy classification, often resulting from the dynamic and sometimes violent interactions between galaxies. For example, lenticular galaxies possess a large central bulge and a disk, but lack the spiral arms, sitting in a category between spiral and elliptical galaxies. This diversity underscores the complexity of cosmic evolution and the influence of gravity, collision, and merger events in shaping the universe's structure. The Milky Way. The structure of the Milky Way, our galactic home, is a marvel of cosmic architecture, embodying the complexity and elegance of the universe's vast expanse. Envisioned as a colossal spiral, our galaxy is a composite of several distinct components, each playing a critical role in its overall makeup and functioning. At its core lies a bulging sphere of stars, enveloping a supermassive black hole known as Sagittarius A, a silent yet influential force driving the galaxy's dynamics. This bulge, dense and packed with stars, some of which are among the oldest in our galaxy, hints at the Milky Way's ancient history and the evolutionary processes that have shaped it. Surrounding the central bulge is the galaxy's disk, a vast plane extending up to 100,000 light-years in diameter, composed of stars, planets, gas, and dust. This disk is not uniform, but is punctuated by spiral arm sites of intense star formation and vibrant cosmic activity. These arms, named after the constellations that can be seen from Earth, such as the Perseus and Sagittarius arms, weave through the galaxy, their patterns believed to be shaped by density waves that compress gas and dust, sparking the birth of new stars. Embedded within the disk is the Sun, our own star, situated in a smaller arm called the Orion Spur, about 27,000 light-years from the galactic center. This location offers us a privileged vantage point from which to observe and study the broader structure of the galaxy, although our view is obscured by interstellar dust and gas, making much of the Milky Way a mystery waiting to be unraveled. Encasing the disk and central bulge is a spherical halo, an extended cloud of stars and globular clusters orbiting the galaxy's core. These clusters are tightly bound groups of stars, relics of the Milky Way's formative years, offering clues to its composition and the processes of galactic evolution. The halo also contains the majority of the galaxy's dark matter, an invisible substance that exerts a gravitational pull, influencing the motion of stars and gas within the galaxy and holding the Milky Way together. Additionally, the Milky Way features a complex system of satellite galaxies, including the large and small Magellanic Clouds, visible from the southern hemisphere. These smaller galaxies, along with others, orbit the Milky Way, engaged in a gravitational dance that, over billions of years, influences their structure and may eventually lead to their merger with our galaxy. The age of the Milky Way, our sprawling galactic home, is a topic that captures the imagination, offering a window into the ancient past of the universe itself. Through the diligent efforts of astronomers and astrophysicists, using a combination of observational data and theoretical models, we've come to understand that our galaxy is approximately 13.6 billion years old. This remarkable age places its formation not long after the Big Bang, which is estimated to have occurred about 8 billion years ago, making the Milky Way one of the universe's older galaxies. Determining the age of the Milky Way involves piecing together evidence from various sources. One of the key methods scientists use is studying the oldest stars within the galaxy. By measuring the abundances of different elements in these stars, researchers can infer their ages. Older stars have fewer heavy elements, as these were formed in the cores of stars and distributed into space as stars died, enriching the galaxy with the materials for new stars. The ages of these ancient stars, many found in the galaxy's halo and in globular clusters, offer clues to the Milky Way's early years. Another approach to gauging the galaxy's age comes from understanding the age of the universe itself, derived from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and the expansion rate of the universe. By comparing the age of the oldest stars with the age of the universe, scientists can confirm that the Milky Way formed early in cosmic history. The age of the Milky Way not only tells us about the longevity of our galaxy, but also provides insights into the processes of galaxy formation and evolution. It suggests that the Milky Way began forming soon after the dawn of the universe, growing over billions of years through the accumulation of gas, the formation of stars, and the merging with other galaxies. This gradual assembly process, influenced by the mysterious dark matter that pervades the galaxy, has shaped the Milky Way into the spiral galaxy we observe today. Understanding the age of the Milky Way also puts into perspective the cosmic timeline on which astronomical events occur. For instance, the Sun, around 6 billion years old, is a relatively young addition to the galaxy, highlighting the ongoing nature of star formation and the dynamic evolution of the Milky Way. The galactic center is a term that evokes a sense of intrigue and mystery, pointing us towards the dense, luminous heart of the Milky Way. This region, bustling with astronomical activity, is located about 27,000 light-years from Earth and houses a remarkable array of cosmic phenomena, central to which is Sagittarius A Cesar A, a supermassive black hole that serves as the dynamo at the core of our galaxy. With a mass equivalent to about 4 million times that of our Sun, SCAR A is the gravitational anchor around which the galaxy's vast spiral structure coalesces. Surrounding this enigmatic black hole is a bustling environment of stars, gas clouds, and other astronomical objects, all tightly packed into a relatively small volume of space. This region teems with a variety of stars, from young, hot blue stars that blaze with intense brightness to older, cooler stars that have orbited the galactic center for billions of years. The presence of young stars in such a hostile environment, close to a supermassive black hole, puzzles astronomers, as the tidal forces exerted by the black hole should theoretically tear apart the gas clouds from which stars form. Yet, their existence suggests that star formation processes in the galactic center are somehow different from those in the galaxy's less tumultuous regions. In addition to stars, the galactic center is awash with vast clouds of gas and dust, some of which are in the process of being pulled into Cesar A, while others may be forming new stars. The region is also crisscrossed by filaments of magnetic energy and bathed in the intense radiation emitted by the accretion of material onto the supermassive black hole, creating a dynamic and complex astrophysical laboratory. The area around the galactic center is also the source of various high-energy phenomena, including flares and other emissions resulting from the interaction of SGR A with its surroundings. These events provide astronomers with valuable insights into the physics of black holes and the mechanisms of energy transfer in the extreme conditions near a galaxy's core. Observing the galactic center is a challenging endeavor due to the vast amounts of interstellar dust that lie between it and Earth, which obscure our view in visible light wavelengths. However, astronomers have employed radio, infrared, and X-ray telescopes to pierce through this veil of dust, revealing the center's complex structure and activity. These observations have not only confirmed the presence of the supermassive black hole, but have also allowed scientists to study the properties of CGR-A and its impact on the galactic center's environment. The Milky Way, our grand spiral galaxy, does not exist in isolation in the vast expanse of the universe. It is accompanied by a retinue of smaller satellite galaxies, each with its own unique characteristics and trajectory, yet all are bound to the Milky Way by the invisible tethers of gravity. These interactions between the Milky Way and its satellites are not merely distant passive relationships, but are dynamic and, at times, tumultuous, playing a significant role in the evolution of our galaxy. Among the most notable of these satellite galaxies are the large and small Magellanic Clouds, visible from the southern hemisphere. These dwarf galaxies, rich in gas and dust, are in a close gravitational dance with the Milky Way, one that has implications for the structure and future of all the galaxies involved. As they orbit our galaxy, gravitational forces act between the Milky Way and the Magellanic Clouds, resulting in phenomena such as tidal stripping, where gas is pulled away from the satellite galaxies. This stripped gas can feed into the Milky Way, contributing to the reservoir of material from which new stars form. Moreover, the interaction between the Milky Way and its satellites is not a one-way street. The gravitational pull of the Magellanic Clouds, for example, has been implicated in the warping of the Milky Way S disk, a subtle yet telling indication of the interconnectedness of cosmic structures. Additionally, these gravitational interactions can spur the formation of tidal streams, elongated trails of stars and gas stripped from the smaller galaxies. These streams, some of which can be traced back to long-lost satellites now fully merged with the Milky Way, provide archaeologists of the sky with clues about the Milky Way's history and its satellite interactions. The Sagittarius dwarf spheroidal galaxy offers another vivid example of these galactic interactions. Currently in the process of being cannibalized by the Milky Way, this small galaxy is being torn apart by our galaxy-S gravitational forces. The remnants of this ongoing merger, in the form of stellar streams wrapping around the Milky Way, are a testament to the dynamic nature of galactic evolution and the eventual fate of many satellite galaxies. These interactions are not merely incidents of cosmic violence, but are fundamental processes that drive the evolution of galaxies. The accretion of satellite galaxies brings fresh gas into the Milky Way, fueling new generations of stars and contributing to the chemical complexity of our galaxy. At the same time, these mergers and interactions help to redistribute matter within the Milky Way, influencing its structure and dynamics. Peering into the future of the Milky Way galaxy unveils a narrative rich with cosmic evolution and dramatic transformations. As astronomers gaze through their telescopes and run simulations on powerful computers, they forecast a future in which the Milky Way undergoes significant changes, shaped by the inexorable forces of gravity, the ongoing process of star formation, and impending galactic collisions. One of the most monumental events predicted to occur in the Milky Way's future is its collision with the Andromeda Galaxy. Currently, Andromeda, also a spiral galaxy like the Milky Way, is about 2.5 million light-years away, but is moving towards us at about 110 kilometers per second. In approximately 4 billion years, the skies above Earth or any planet hosting observers at that time will bear witness to this grand cosmic merger. As these two galaxies begin to intertwine, their mutual gravitational forces will draw them closer, eventually merging into a single, larger elliptical galaxy, sometimes humorously dubbed Milkomeda or Milkydromeda in scientific discussions. This merger is not expected to be a cataclysmic destruction of either galaxy, but rather a complex dance of stars and gas clouds. Given the vast distances between stars, direct collisions are unlikely. Instead, the gravitational interactions will send stars and planetary systems into new orbits, possibly ejecting some from the newly formed galaxy altogether. The gas clouds within the galaxies, however, will collide, leading to intense bursts of star formation, lighting up the merging galaxies with new stellar nurseries. Following the merger, the center of the newly formed galaxy will be dominated by the combined mass of the Milky Way S and Andromeda S supermassive black holes. These colossal black holes will gradually spiral towards each other and eventually merge, releasing vast amounts of energy and possibly sending ripples through the fabric of space-time itself in the form of gravitational waves. In the long term, the future of the Milky Way, like that of all galaxies, will also be influenced by the life cycles of its stars. As stars exhaust their nuclear fuel, they will evolve through their life stages, with massive stars exploding as supernova and less massive stars shedding their outer layers to form planetary nebulae. Over trillions of years, this will leave behind a galaxy populated by dim white dwarfs, neutron stars, and black holes. Moreover, the universe's continuous expansion will have a profound effect on the Milky Way's future. Distant galaxies will recede far beyond our observational reach, making the universe appear increasingly empty from our vantage point. However, the gravitational bond between the Milky Way and its local group of galaxies will keep these cosmic neighbors together, forming a small oasis of matter in an accelerating, expanding universe. The Solar System. The formation of the Solar System is a captivating chapter in the story of the cosmos, revealing the processes that led to the creation of our Sun, the planets, and the myriad smaller bodies that orbit our star. This cosmic tale began around 6 billion years ago in a dark corner of the Milky Way when a vast cloud of gas and dust, known as the Solar Nebula, started to collapse under its own gravity. This collapse was likely triggered by the shockwave from a nearby supernova, which injected energy into the cloud, causing it to compress. As the nebula collapsed, it began to spin, flattening into a rotating disk with the densest material gathering at the center. This process of accretion led to the formation of a protostar at the heart of the disk, which would eventually ignite to become our Sun, fueled by nuclear fusion reactions converting hydrogen into helium. Surrounding the newborn Sun, the remaining material in the disk began to coalesce. Through a process known as accretion, particles collided and stuck together, gradually building up to form the larger bodies of the solar system. Closer to the Sun, where temperatures were higher, metals and silicates were able to condense, forming the terrestrial planets Mercury, Venus, Earth, and Mars. These rocky bodies are composed mainly of silicate rocks and metals, with Earth being the only one to harbor life as we know it. Further out, beyond the so-called frost line, where temperatures were cold enough for ice to remain solid, gas giants and ice giants began to form. Here, planets like Jupiter and Saturn were able to accumulate massive amounts of hydrogen and helium, growing to enormous sizes, while Uranus and Neptune, the ice giants, gathered their bulk from water, ammonia, and methane ices. The outermost regions of the solar system saw the formation of the Kuiper Belt and the Oort cloud, home to countless icy bodies, comets, and dwarf planets such as Pluto. These objects are remnants of the early solar system, largely unchanged since their formation. One of the most fascinating aspects of the solar system's formation is the role of Jupiter, the largest planet. Its immense gravity influenced the orbits of other bodies, shaping the architecture of the solar system and possibly flinging some objects into the Sun or out into the vastness of space. Throughout billions of years, the solar system has been a dynamic and evolving place, marked by collisions and migrations that have shaped the planets and their orbits. The late heavy bombardment, a period of increased comet and asteroid impacts about 8 billion years ago, is one example of the dramatic events that have left their mark on the solar system. In understanding the formation of the solar system, scientists rely on a combination of observational data, computer simulations, and the study of meteorites, which provide direct evidence of the early solar system's composition. These investigations not only shed light on our cosmic origins, but also offer insights into the formation of other planetary systems across the galaxy. The Milky Way, our galaxy, played an indispensable role in the formation of the solar system, setting the stage for the series of events that led to the birth of the Sun and its surrounding planets, moons, asteroids, and comets. This grand cosmic narrative is rooted in the Milky Way's vast reservoirs of gas and dust, its gravitational forces, and the life cycles of its stars, which together fostered the conditions necessary for the solar system's emergence about 6 billion years ago. At the heart of the solar system's formation story is the interstellar medium of the Milky Way, a mixture of gas, mostly hydrogen and helium, along with dust. This medium, enriched over billions of years by the remnants of dead stars, provided the raw materials from which the solar system was formed. Supernovae, the explosive deaths of massive stars, played a crucial role by seeding the galaxy with heavy elements like carbon, oxygen, and iron, which are essential for the formation of rocky planets and the development of life on Earth. The Milky Way-S gravitational landscape also influenced the Solar System S formation. The Galaxy S spiral structure, characterized by its rotating arms, is thought to trigger the formation of new stars as it sweeps through the interstellar medium, compressing gas and dust. It exists within such a dynamic environment that our solar system found its origin in a dense region of a molecular cloud where the conditions were just right for the solar nebula, the cloud of gas and dust that collapsed to form the Sun and its planets to coalesce. Furthermore, the Milky Way-S chemical composition, a record of its history of star formation and death, provided a critical backdrop. The particular mix of elements available in the region of the galaxy where the solar system formed influenced the types of planets that could emerge. The inner, rocky planets Mercury, Venus, Earth, and Mars formed from materials that could condense at the high temperatures close to the young Sun. In contrast, the gas giants and ice giants formed farther out, where cooler conditions allowed for the accumulation of volatile compounds. The Solar System S location within the Milky Way is another aspect of the Galaxy S role in its formation. Situated in the Orion Arm, a relatively quiet region between the major spiral arms, the solar system has been spared from the intense radiation and gravitational disturbances that might disrupt planetary systems closer to the Galaxy S bustling center. This stable environment has been conducive to the development and persistence of life on Earth, providing a vantage point from which we can observe and study the galaxy and the broader universe. The formation of Earth is a chapter in the grand narrative of the Solar System S birth, unfolding over 6 billion years ago within the swirling disk of gas and dust known as the solar nebula. This process, driven by the laws of physics and the dynamic environment of the early solar system, led to the creation of our home planet, a world uniquely suited for life as we know it. As the solar nebula collapsed under its own gravity, it spun faster and flattened into a disk. At the center, the Sun began to form, igniting its nuclear furnace and casting light and heat out into the surrounding space. In the cooler regions of the disk, far enough from the young Sun's warmth, particles of dust and ice began to stick together as they collided, forming clumps that grew into larger bodies over time. These early building blocks of the planets, known as planetesimals, continued to collide and merge, driven by their mutual gravitational attraction. In a process termed accretion, these planetesimals gradually built up the rocky cores of the inner planets, including Earth. This early phase of Earth-S formation was marked by intense bombardment as it grew through the accumulation of material, reaching about 60 of its current size relatively quickly in a few tens of millions of years. As Earth grew, its interior heated up due to the energy released from these collisions, along with the decay of radioactive elements within its materials. This heat caused the young Earth to partially melt, allowing it to differentiate into layers: a dense metallic core, a silicate mantle, and a crust on the surface. The formation of Earth-S core was crucial for generating the planet-S magnetic field, which plays a key role in protecting the surface from harmful solar and cosmic radiation. Meanwhile, the intense heat and volcanic activity released gases trapped in the rocks, contributing to the formation of Earth-S early atmosphere. Water vapor, carbon dioxide, methane, and ammonia were among the gases released, creating a primordial atmosphere very different from the one we breathe today. Water vapor in the atmosphere eventually condensed as the Earth cooled, falling as rain and filling the basins that formed on the planet's surface, creating the oceans. The presence of liquid water, essential for life, along with the stability provided by Earth's size, orbit, and its protective magnetic field, set the stage for the eventual emergence of life. Over billions of years, Earth's atmosphere and surface evolved. The emergence of life, particularly photosynthetic organisms, transformed the atmosphere, increasing the amount of oxygen and making it hospitable to a diverse range of life forms. These biological and geological processes have continued to shape Earth, making it the dynamic, life-supporting planet we know today. The emergence of life on Earth, a planet teeming with diverse forms of organisms, is the result of a unique combination of conditions and events that unfolded over billions of years. These conditions, ranging from the planet's placement in the solar system to the composition of its atmosphere and oceans, created an environment conducive to the development and sustenance of life as we know it. One of the most fundamental conditions that made life possible on Earth is its location in the solar system, often referred to as the Goldilocks zone or the habitable zone. This region is not too close to the Sun, where it would be too hot for liquid water to exist, and not too far, where it would be too cold. Earth's orbit within this zone allowed for the presence of liquid water on its surface, a critical ingredient for life. The formation of Earth's atmosphere was another crucial step in creating a habitable planet. Initially composed of gases released from volcanic eruptions, such as water vapor, carbon dioxide, and ammonia, the atmosphere underwent significant changes over time. The emergence of photosynthetic organisms, which could convert carbon dioxide and water into oxygen and glucose using sunlight, gradually increased the oxygen levels in the atmosphere. This oxygen-rich atmosphere not only supported the development of new life forms, but also formed the ozone layer, which protects the surface from harmful ultraviolet radiation from the sun. Earth's magnetic field, generated by the movement of molten iron in its outer core, shields the planet from solar and cosmic radiation that could strip away the atmosphere and harm living organisms. This protective field ensures that the atmosphere remains intact and provides a stable environment for life. Moreover, Earth's geological activity has played a significant role in creating conditions favorable for life. Plate tectonics, the movement of the Earth's lithospheric plates, has led to the formation of continents and ocean basins, the recycling of carbon through the carbon-silicate cycle, and the regulation of the planet's temperature. This dynamic geological activity has also facilitated the distribution of minerals and nutrients essential for life, creating diverse habitats and environments. The presence of water in all three states, solid, liquid, and gas on Earth's surface, is another condition pivotal to life. Water is a solvent, facilitating chemical reactions necessary for life, and its unique properties, such as its ability to dissolve a wide range of substances, have been crucial in the development of complex biological molecules. Lastly, Earth's natural satellite, the Moon, has contributed to the stability of the planet's climate by stabilizing its axial tilt, which influences seasonal variations. The relatively mild and stable climate resulting from this axial tilt has allowed for a wide range of ecosystems to flourish over millions of years. Advanced topics. Dark energy, a term that evokes mystery and intrigue, plays a pivotal role in the cosmos, fundamentally influencing the universe's fate and structure. This enigmatic force, which makes up about 68% of the universe, is responsible for the accelerated expansion of the universe, a discovery that has reshaped our understanding of cosmology since it was first observed in the late 1990s. The concept of dark energy emerged from observations of distant supernovae, which showed that galaxies are moving away from each other at an accelerating rate, contrary to the expectation that the universe's expansion should be slowing down due to gravity. This acceleration suggested the presence of an unknown form of energy that permeates all of space, exerting a repulsive force that overcomes gravity on cosmological scales. Dark energy's role in the universe is still not fully understood, and it remains one of the most profound mysteries in physics. However, its effect on the universe's expansion is a key aspect of its influence. By accelerating the expansion, dark energy impacts the structure of the universe, affecting the formation and evolution of galaxies. Without dark energy, the universe might have collapsed back on itself under gravity or expanded much more slowly, leading to a very different cosmic landscape. One of the leading theories about the nature of dark energy is the cosmological constant, a concept introduced by Albert Einstein as a modification to his theory of general relativity. The cosmological constant represents a density of energy that fills space, with a constant value that does not change over time. Another possibility is that dark energy is a dynamic field, similar to an electromagnetic field, with properties that vary across space and time. This scenario could lead to a changing rate of cosmic expansion and even to future changes in the universe's fate. The presence of dark energy also has implications for the ultimate fate of the universe. If its density remains constant or increases over time, the universe could continue to expand indefinitely, becoming colder and emptier as galaxies drift apart. Alternatively, if dark energy changes in a way that strengthens its repulsive force, the universe could end in a big rip, where galaxies, stars, and even atoms are torn apart by the accelerating expansion. Understanding dark energy is not only crucial for cosmology, but also for fundamental physics, as it challenges existing theories and may hold the key to new laws of nature. Scientists are actively researching dark energy through observations of the cosmic microwave background, the distribution of galaxies and supernovae, as well as through experiments designed to probe the nature of space and energy. Galaxies, the vast assemblies of stars, gas, dust, and dark matter that populate the universe, are not static entities but are instead constantly evolving. This evolution is a slow process on human timescales, unfolding over billions of years, driven by a variety of cosmic forces and phenomena. Understanding how galaxies evolve is key to unlocking the secrets of the cosmos, revealing the life cycle of the universe as fundamental building blocks. The evolution of galaxies is influenced by their initial mass, the environment in which they reside, and the interactions they have with other galaxies and intergalactic matter. In the early universe, shortly after the Big Bang, galaxies began as small protogalaxies, which grew over time through the accretion of gas and the mergers with other protogalaxies. These processes contributed to the diversity of galaxy shapes and sizes observed today, from spiral galaxies like the Milky Way to elliptical and irregular galaxies. For spiral galaxies, star formation plays a crucial role in their evolution. The spiral arms, rich in gas and dust, are sites of active star formation, where new stars are born from the gravitational collapse of gas clouds. Over time, as these galaxies use up or lose their interstellar gas to star formation or ejections from supernovae, their rate of new star formation decreases. This leads to a gradual aging of the stellar population, as older, redder stars dominate the galaxy-S appearance. Elliptical galaxies, on the other hand, often result from the mergers of smaller galaxies. These catastrophic events can trigger bursts of star formation as gas clouds collide and collapse, but they also tend to scatter and heat up gas, making it less likely to form new stars in the future. As a result, elliptical galaxies typically contain older, redder stars and have less interstellar gas available for star formation compared to their spiral counterparts. Galaxy interactions, including mergers and close encounters, are another significant driver of galactic evolution. These interactions can profoundly affect a galaxy-S structure and star formation rate. For instance, when two galaxies of similar size merge, they can form a larger elliptical galaxy, disrupting the original spiral structure and triggering a short-lived but intense period of star formation. Gravitational interactions with nearby galaxies can also distort a galaxy S-shape, leading to the formation of features like tidal tails or bridges. Additionally, galaxies evolve through internal processes such as the feedback from supernovae and active galactic nuclei (AGN). Supernovae can inject energy into the interstellar medium, heating it and driving out gas, which can inhibit further star formation. AGN, powered by material accreting onto a supermassive black hole at a galaxy S center, can also expel large amounts of gas from the galaxy, affecting its ability to form new stars. As galaxies age, their star formation rates generally decline, leading to an older and redder stellar population. This process is influenced by the galaxy S environment, with galaxies in denser regions, such as the centers of galaxy clusters, often evolving faster due to more frequent interactions and the stripping of gas by the hot intracluster medium. Galaxy collisions, a dramatic and fundamental aspect of cosmic evolution, play a pivotal role in shaping the universe. These colossal events occurring over hundreds of millions of years are not merely spectacles of cosmic scale, but are key processes that drive the evolution of galaxies, influence their structure, and ignite star formation, profoundly impacting the cosmos. When galaxies collide, the gravitational forces between them lead to a complex interplay of interactions that can alter their shapes, spark new generations of stars, and even result in the formation of entirely new types of galaxies. Despite the vast distances between stars within galaxies, the immense gravitational forces at play redistribute the gas, dust, and stars, creating intricate patterns and structures such as tidal tails, rings, and bridges. One of the most significant outcomes of galaxy collisions is the trigger of starburst events. As galaxies merge, their interstellar gas clouds can be compressed, leading to regions of intense star formation. These starbursts can give birth to millions of new stars over a relatively short period, dramatically changing the appearance and composition of the resulting galaxy. This process is crucial for understanding the life cycle of galaxies and the distribution of elements essential for life, as these new stars will eventually synthesize heavier elements in their cores. Furthermore, galaxy collisions can lead to the formation of supermassive black holes at the centers of galaxies. The merging of galaxies brings their central black holes closer together, eventually leading to their collision and merger. This process can release vast amounts of energy and influence the dynamics of the surrounding galaxy, including regulating the rate of star formation. Galaxy collisions are also instrumental in the formation of elliptical galaxies. Many astronomers believe that elliptical galaxies, which lack the defined structure and spiral arms of spiral galaxies, are the result of mergers between spiral galaxies. These mergers mix the stars and gas of the original galaxies, resulting in the smoother, more uniform appearance of elliptical galaxies. On a larger scale, galaxy collisions and mergers are a fundamental aspect of the hierarchical model of galaxy formation, a theory that describes how galaxies form and evolve through the accumulation of smaller systems. This process has been occurring since the early universe and continues to shape the large-scale structure of the cosmos, influencing the distribution and evolution of galaxies within clusters and superclusters. The significance of galaxy collisions extends beyond the immediate changes they bring about. They are a testament to the dynamic and ever-changing nature of the universe, providing astronomers with critical insights into the processes of cosmic evolution, the behavior of dark matter, and the gravitational forces that govern the cosmos. Observations and simulations of galaxy collisions not only help us understand the past and present of the universe, but also offer glimpses into its future, as our own Milky Way is on a collision course with the Andromeda Galaxy, promising a spectacular merger in about 4 billion years. Predicting the future of the universe is an endeavor that sits at the heart of cosmology, combining observations, theoretical physics, and simulations to peer into the cosmic depths of time. While certainty in prediction remains elusive due to the complexities and unknowns of cosmic physics, scientists have developed several theories based on our current understanding of the universe as fundamental laws and components, including dark energy, dark matter, and the force of gravity. One of the key factors in these predictions is the role of dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy continues to dominate the universe's energy budget, as it does today, the universe will likely continue expanding indefinitely. In this scenario, known as the Big Freeze or heat death, galaxies will move away from each other increasingly fast. Star formation will gradually cease as galaxies use up their gas reserves, and the universe will cool as it expands. Eventually, stars will burn out, leaving behind white dwarfs, neutron stars, and black holes, which will slowly fade away. Over an unimaginably long timescale, the universe will become a cold, dark, and lifeless expanse, with isolated remnants drifting apart. Another possible scenario is the Big Rip, where dark energy S influence grows over time, leading to an ever-accelerating expansion that eventually tears apart galaxies, stars, planets, and even atomic structures. In this extreme case, the fabric of space-time itself would be ripped apart, culminating in a singularity where the laws of physics as we know them break down. Conversely, if dark energy were to decrease or change its nature, the universe might follow a different fate, such as the Big Crunch. In this scenario, the expansion of the universe would eventually slow down and reverse, leading to a contraction phase. Galaxies, stars, and planets would move closer together, temperatures would rise, and the universe could collapse back into a hot, dense state, potentially leading to another Big Bang and a cyclic model of the universe. Lastly, the fate of the universe could be influenced by the nature of dark matter, the unseen substance that makes up about 27% of the universe's mass energy content. If dark matter particles are discovered and understood, they could reveal new insights into the long-term dynamics of cosmic structures. Predicting the future of the universe is a profoundly complex and speculative endeavor, yet it remains a central question in cosmology, driving scientific inquiry and expanding our understanding of the cosmos. Over trillions of years, stars will exhaust their fuel and leave behind remnants such as white dwarfs, neutron stars, and black holes. Eventually, even these remnants may decay or be consumed by larger black holes, leading the universe to a cold, dark, and empty state. This process includes the evaporation of black holes over vast time spans due to Hawking radiation. Another scenario depends on the nature of dark energy. If dark energy increases in strength over time, it could result in the Big Rip. In this scenario, dark energy's repulsive force would become so dominant that it would tear apart galaxies, stars, planets, and even atoms, culminating in a cataclysmic end for the universe. Alternatively, if the universe contains sufficient matter, including dark matter, to counteract the expansion driven by dark energy, it could begin to contract, leading to a Big Crunch. This scenario envisions the universe reversing its expansion, eventually collapsing in a mirror image of the Big Bang, potentially leading to a new universe in a cyclical process. The Big Bounce is a related theory suggesting that the universe could undergo cycles of expansion and contraction. According to this idea, the current expansion phase following a Big Bang might eventually reverse, leading to a Big Crunch, which then sparks another Big Bang, perpetuating the cycle. This concept is tied to quantum gravity theories and remains speculative, pending further evidence and theoretical development. Predicting the future of the universe involves understanding the fate of cosmic structures like galaxies, stars, and black holes. Over time, galaxies will evolve, stars will deplete their nuclear fuel, and black holes will dominate the cosmic landscape before potentially evaporating through Hawking radiation, given sufficient time. These scenarios are based on our current understanding of cosmological principles and observations. As our knowledge deepens and new observations are made, especially regarding dark energy and dark matter, our predictions about the universe's fate may change. Nonetheless, these cosmological forecasts highlight the dynamic and ever-changing nature of the universe, offering glimpses into the profound questions that drive the field of cosmology. Observational astronomy. Astronomers venture into the universe using sophisticated techniques to observe distant galaxies and stars, unraveling cosmic mysteries. Central to these endeavors are telescopes, not just the kind used by amateur astronomers, but colossal instruments equipped with cutting-edge technology. These telescopes are stationed globally and even beyond Earth's atmosphere to capture the faintest whispers of light from billions of light-years away. The light from these distant celestial bodies carries the secrets of the universe. By analyzing this light, scientists can determine not only the composition of stars and galaxies, but also their distance from us, age and velocity in the cosmic dance of the universe. This analysis is possible through spectroscopy, a technique that breaks down light into its component colors, much like a prism turning sunlight into a rainbow. Each color corresponds to a specific wavelength of light, with certain wavelengths characteristic of specific elements. By studying the spectral lines, astronomers can discern the chemical makeup of distant stars and galaxies. Moreover, the shift of these spectral lines towards the red or blue end of the spectrum, known as the redshift or blue shift respectively, tells us if the object is moving away from or towards us, and at what speed. This phenomenon, rooted in the Doppler effect, has profound implications for our understanding of the universe. Observations of the redshift in light from distant galaxies led to the groundbreaking discovery of the expanding universe, a cornerstone of modern cosmology. Technological advancements have further expanded our cosmic horizons. The Hubble Space Telescope, orbiting Earth, has sent back images of unprecedented clarity, revealing intricate structures of distant galaxies and nebulae. Its successor, the James Webb Space Telescope, aims to observe the first galaxies formed after the Big Bang. These space-based observatories evade the distortions of Earth's atmosphere, allowing for sharper and more detailed observations. Radio telescopes offer a different perspective on the cosmos by capturing radio waves emitted by celestial objects. These giant dishes detect phenomena invisible to optical telescopes, such as the cosmic microwave background radiation, the afterglow of the Big Bang, providing critical insights into the universe's earliest moments. Integrating observations from telescopes operating across the electromagnetic spectrum from radio to gamma rays offers a more complete picture of the universe. This multi-wavelength astronomy has led to the discovery of phenomena such as quasars and pulsars, further enriching our understanding of cosmic evolution. Advanced observational technologies. Beyond traditional designs, modern telescopes incorporate various technologies to enhance their capabilities. Adaptive optics compensates for Earth's atmospheric blurring by making rapid adjustments to the shape of the telescope's mirror or using additional optics. This system relies on measurements from a reference star or an artificial laser guide star to determine atmospheric distortion and correct for it in real time, allowing for sharper images of celestial objects. Interferometry combines the light collected by multiple telescopes to create a single, more detailed image, dramatically increasing its resolution. The Very Large Telescope VLT in Chile and the Atacama Large Millimeter-Submillimeter Array ALMA use interferometry to study the birth of stars, the formation of planetary systems, and the intricate structures of distant galaxies with unprecedented clarity. Radio astronomy continues to be a cornerstone of our quest to understand the galaxy. Unlike optical telescopes that capture visible light, radio telescopes detect radio waves emitted by celestial objects, observing phenomena otherwise invisible, such as the cosmic microwave background radiation or mysterious fast radio bursts from deep space. The Square Kilometer Array SKA, an international effort to build the world's largest radio telescope, promises to revolutionize our understanding of the universe, from exploring its early epochs to mapping galaxy distribution. Space missions and satellites play an indispensable role in galactic studies. Satellites like the Gaia Observatory map the positions and movements of billions of stars in the Milky Way, providing data essential for understanding the structure, formation, and evolution of our galaxy. Missions like Kepler and TESS Transiting Exoplanet Survey satellites scour the galaxy for exoplanets, offering insights into the potential for life elsewhere in the universe. Computational astronomy has become an increasingly vital tool in the astronomer's arsenal. The vast amounts of data generated by various observational technologies are analyzed and interpreted using sophisticated computer models and simulations. These computational tools allow scientists to test theories about galaxy formation, black hole behavior, and cosmic evolution in ways previously unimaginable. The mechanics of telescopes. Delving deeper into the heart of astronomical discovery, the working of telescopes unfolds as a tale of human ingenuity, enabling us to extend our sight far beyond Earth's confines. At their core, telescopes serve as the eyes into the universe, designed to collect and magnify light from celestial objects so distant they appear as mere pinpricks of light in the night sky. The principle behind telescopes is rooted in optics, the branch of physics that deals with light's behavior and properties. There are two primary types of telescopes used by astronomers: refracting and reflecting. Refracting telescopes use lenses to bend or refract light. When light from a distant star enters the telescope, it passes through the objective lens at the front of the telescope. This lens gathers the light and bends it to a specific point, the focal point. At the focal point, the light rays converge and form an image, which can be magnified and examined through the eyepiece lens at the other end. The larger the objective lens, the more light the telescope can collect, and the better its ability to reveal faint objects in the night sky. Reflecting telescopes use mirrors instead of lenses to collect and focus light. A typical reflecting telescope has a large, curved primary mirror at the bottom of the telescope that reflects incoming light to a focal point. Before the light reaches this focal point, it is intercepted by a smaller secondary mirror, which redirects the light to an eyepiece or a detector, such as a camera or a spectrograph, where the image is formed. Reflecting telescopes avoid chromatic aberration, a type of distortion that occurs in refracting telescopes because lenses bend different colors of light by different amounts. Modern telescopes incorporate various technologies to enhance their capabilities. Adaptive optics, for instance, compensates for the blurring effects of Earth's atmosphere by making rapid adjustments to the shape of the telescope's mirror or by using additional optics. This system relies on measurements from a reference star or an artificial laser guide star to determine atmospheric distortion and correct for it in real time, allowing for sharper images of celestial objects. The effectiveness of a telescope is not solely determined by its magnification, but also by its resolving power, the ability to distinguish between objects close together in the sky. This power is influenced by the diameter of the telescope's mirror or lens. The larger the diameter, the finer the details it can resolve. Astronomical discoveries. The last century has been unparalleled in its contributions to astronomical discovery, each finding peeling back layers of the universe's mysteries. The discoveries have reshaped our understanding and expanded the realms of possibility. One of the most profound discoveries was the expansion of the universe, emerging from observing the redshift in the light from distant galaxies. This observation, indicating that galaxies are moving away from us in all directions, led to the Big Bang theory, suggesting the universe began from a singular, incredibly dense and hot state and has been expanding ever since. This foundational theory, dating back to the 1920s, has shaped our understanding of cosmological evolution and the dynamic nature of the cosmos. The discovery of cosmic microwave background radiation in 1965 further bolstered the Big Bang theory. This faint glow, detected almost uniformly in all directions, is the afterglow of the universe's infancy, offering a snapshot of the cosmos just 380,000 years after the Big Bang, before stars and galaxies formed. Its detection provided concrete evidence of the universe's hot, dense beginnings and its subsequent rapid expansion. Another landmark discovery was the first observation of a black hole. While the existence of black holes was predicted by Einstein's theory of general relativity in the early 20th century, it wasn't until 1971 that astronomers identified what is now considered the first black hole, Cygnus X1. This finding was a monumental leap in our understanding of the universe and most enigmatic objects, regions of space where gravity is so strong that not even light can escape. The exploration of exoplanets, planets outside our solar system, has been a major area of discovery in recent decades. The first confirmed detection in 1992 of planets orbiting a pulsar, and the subsequent discovery in 1995 of a planet orbiting a sun-like star have opened a new frontier in astronomy. These discoveries have led to a surge in exoplanet research, with thousands now identified, challenging our ideas about planetary systems and their formation, and fueling the quest for understanding the potential for life beyond Earth. The Hubble Space Telescope, launched in 1990, has been instrumental in many of the era's significant discoveries. Its observations have led to breakthroughs in our understanding of the age of the universe, the existence of dark energy, a mysterious force accelerating the expansion of the universe, and the detailed properties of galaxies, stars, and planets far beyond our solar system. In recent years, the detection of gravitational waves, ripples in the fabric of space-time caused by catastrophic events such as merging black holes, has opened a new window into the cosmos. First observed in 2015, this discovery confirmed a major prediction of Einstein's theory of general relativity and introduced a new method of observing cosmic events, providing insights into phenomena otherwise invisible through traditional electromagnetic observation. Theoretical astrophysics. Theoretical models are the scaffolding upon which our understanding of the universe is built, offering profound insights into the cosmos that stretch beyond the reach of current observational capabilities. These models serve as a bridge between the concrete world of observation and the abstract realm of what could be, enabling scientists to predict phenomena yet to be seen and providing explanations for those observed. At their core, theoretical models are grounded in mathematics and physics, embodying principles governing everything from the smallest particles to the largest structures in the universe. The Standard Model of Particle Physics describes the fundamental particles and forces that constitute the universe. This framework has been instrumental in predicting the existence of particles before they were detected experimentally, such as the Higgs boson, discovered in 2012. The Higgs boson was pivotal, providing evidence for the mechanism that gives particles mass. This discovery was a triumph for theoretical physics, showcasing the power of models to guide empirical research. Einstein's theory of general relativity is another monumental theoretical model that has shaped our understanding of the universe. General relativity describes how gravity is not merely a force between masses, as Newton proposed, but rather a curvature of space-time caused by mass and energy. This theory predicts phenomena such as the bending of light by gravitational lensing, the orbit of Mercury, and the existence of black holes, predictions confirmed through observations. General relativity laid the groundwork for understanding cosmic expansion and provided the theoretical framework for the detection of gravitational waves, a prediction made by Einstein nearly a century before it was experimentally confirmed. Theoretical models also play a crucial role in understanding the universe's large-scale structure and its evolution. The Lambda CDM model, incorporating dark matter and dark energy, offers a comprehensive explanation for the formation and distribution of galaxies, the cosmic microwave background radiation, and the accelerating expansion of the universe. Through numerical simulations based on this model, astronomers can recreate the universe's evolution from shortly after the Big Bang to its current state, offering insights into how galaxies cluster and how large-scale structures form. Moreover, theoretical models are indispensable in studying phenomena currently beyond our observational reach. For example, theories of cosmic inflation propose a period of exponential expansion in the early universe, solving several cosmological puzzles like the uniformity of the cosmic microwave background radiation across vast distances. Although direct evidence for inflation is still sought, the theoretical framework fits well with existing observations and has guided the search for new empirical data. The interplay between theoretical models and observations is a dynamic and iterative process. Models predict phenomena that guide the design of experiments and observations, while unexpected findings from these observations can challenge existing models, prompting refinements or new theories. This symbiotic relationship drives the progress of cosmological science, continually refining our understanding of the universe. Simulations in astrophysics. Simulations in astrophysics act as a digital cosmos, a realm where scientists can explore the intricacies of the universe in ways that physical experiments cannot. These simulations are sophisticated computer programs modeling astrophysical processes, allowing researchers to study the behavior of galaxies, stars, planets, and other celestial phenomena over time. By inputting the laws of physics and initial conditions into these simulations, astrophysicists can watch cosmic events unfold in a virtual universe, providing insights into the dynamics of the cosmos beyond our reach. The power of simulations lies in their ability to handle the complexity and vast scales of space and time inherent in astrophysical phenomena. For instance, the formation of galaxies, a process spanning billions of years and involving gravity, gas dynamics, star formation, and feedback from supernovae and supermassive black holes, can be modeled through simulations. These digital experiments allow scientists to vary parameters such as dark matter density or star formation rate to see how these changes affect galaxy evolution. This not only helps understand how our galaxy and its neighbors formed, but also predicts how they might evolve in the future. Simulations also play a crucial role in testing theories of the universe's large-scale structure. The cosmic web, a vast network of interconnected filaments of dark matter forming the universe's backbone, is extensively studied through simulations. By comparing these simulated structures with observations from telescopes and surveys, scientists refine their understanding of dark matter and the forces shaping the universe. In studying planet formation and the search for extraterrestrial life, simulations offer a window into the processes leading to the birth of planets and their atmospheres. These models explore various scenarios for how planets form around stars, the conditions for habitable environments, and the potential signatures of life that future missions could search for. This theoretical groundwork guides the design of telescopes and missions aimed at finding Earth-like planets and investigating their atmospheres. Simulations are invaluable in studying cosmic events such as supernovae, black hole mergers, and galaxy collisions. These cataclysmic events can be modeled in detail, predicting gravitational waves, the distribution of elements forged in supernovae, or the intricate dance of galaxies merging over billions of years. These predictions can then be tested against observations, providing a powerful tool for verifying theories about the universe as most energetic events. Simulations in astrophysics bridge theory and observation, offering a controlled environment to test the laws of physics against the cosmos' vastness. They enable scientists to explore the universe's past, understand its present, and predict its future, pushing the boundaries of our knowledge and bringing us closer to unraveling the cosmos' mysteries. Modeling the formation of galaxies. Modeling. The formation of galaxies merges the art of simulation with astrophysics precision, offering a window into the birth and evolution of these colossal structures. Computational models incorporate the laws of physics to simulate the complex interplay of matter and energy leading to galaxy formation. These models begin with the early universe conditions just after the Big Bang and evolve forward in time, allowing scientists to observe how galaxies might have formed and changed over billions of years. Galaxy formation is influenced by multiple factors, including dark matter distribution, gas cooling and condensation into stars, black hole formation at galaxy centers, and feedback from stars and supernova. Numerical simulations are powerful tools in this field. They create virtual universes within supercomputers, where particles represent dark matter, gas, stars, and other components. The simulations use equations derived from gravity, thermodynamics, and hydrodynamics laws to describe how these particles interact over time. By adjusting initial conditions and physical laws, scientists can explore how different factors influence galaxy formation and compare outcomes with telescope observations to test their models' accuracy. Dark matter, an invisible substance that does not emit, absorb, or reflect light but exerts gravitational forces, plays a crucial role in galaxy formation. Dark matter forms the cosmic web structure, with dense regions attracting baryonic matter, normal matter that makes up stars, planets, and life through gravity. The early universe's dark matter distribution is often modeled based on cosmic microwave background radiation observations, showing the matter distribution 380,000 years after the universe began. As the universe evolves in these simulations, dark matter clumps together, forming dense regions called dark matter halos. Gas falls into these halos, cools, and condenses to form stars and galaxies. Feedback processes from stars, such as supernova explosions and massive star winds, are also modeled, as they can eject gas from galaxies and regulate further star formation. These galaxy formation models are continually refined as new astronomical observations provide additional data on galaxies' properties at various stages of the universe's history. Observations of distant galaxies allow scientists to look back in time and see galaxies as they were billions of years ago, providing critical tests for the models. Mysteries and unknowns. Despite significant strides in understanding the cosmos, several fundamental puzzles challenge our grasp of the universe. A few stand out for their profound implications on physics, astronomy, and our place in the cosmos. One of the most intriguing questions is the nature of dark matter. Although it constitutes about 85% of the universe's total matter, dark matter neither emits nor absorbs light, making it invisible and detectable only through its gravitational effects on visible matter. Its exact composition remains one of the biggest mysteries in cosmology. Various candidates have been proposed, including weakly interacting massive particles WIMPs and axions, yet despite extensive searches, dark matter has eluded direct detection, leaving its true nature a profound mystery. Equally perplexing is the puzzle of dark energy, which accounts for approximately 70% of the universe's total energy content. Dark energy is thought to be responsible for the accelerated expansion of the universe, a discovery that upended previous notions of a slowly decelerating cosmos. Understanding what dark energy is and how it behaves could revolutionize our understanding of the universe's fate, yet it remains one of the most elusive aspects of modern cosmology. Another major question involves the universe's rate of expansion, known as the Hubble constant. Observations of distant galaxies and the cosmic microwave background radiation have provided different measurements of this rate, leading to a discrepancy that cannot be easily resolved. This inconsistency suggests new physics beyond our current understanding, possibly related to dark matter, dark energy, or another unknown factor influencing the universe's expansion. The mystery of the universe's initial conditions, including the cause of the Big Bang and the nature of cosmic inflation, also looms large. Cosmic inflation theory proposes a period of exponential expansion in the first fractions of a second after the Big Bang, setting the stage for the universe's evolution. However, what triggered inflation and how it proceeded remains unclear, with several competing models and no consensus on the exact mechanism. Lastly, the question of why there is more matter than antimatter in the universe puzzles scientists. Theories predict that the Big Bang should have produced equal amounts of matter and antimatter, which would annihilate upon contact, leaving behind a universe filled with light but little else. Yet, we exist in a universe dominated by matter, indicating an asymmetry in the laws of physics that favored the creation of matter over antimatter. Unraveling this mystery could shed light on the fundamental forces and conditions of the early universe. Dark matter and dark energy. Dark matter and dark energy are two of the most captivating chapters in modern cosmology. These invisible constituents of the universe pose profound mysteries as they do not interact with electromagnetic forces, meaning they neither emit nor absorb light, rendering them invisible and detectable only through their gravitational effects. Dark matter, making up about 85% of the universe's total matter, is perceived through its gravitational pull on galaxies and galaxy clusters. Unlike ordinary matter, which can be observed through telescopes due to the light it emits or reflects, dark matter does not interact with light. Its presence is inferred from phenomena such as the rotation speeds of galaxies and the way light bends as it travels through the universe, known as gravitational lensing. The rotation speeds of galaxies, for instance, are far greater than expected based on the visible matter alone, suggesting the presence of a substantial amount of unseen mass. Despite its invisibility, dark matter plays a critical role in the universe's structure and evolution, helping to bind galaxies together and influencing their formation and movement. The nature of dark matter remains one of the biggest unanswered questions in science. Various hypothetical particles have been proposed as dark matter candidates, including weakly interacting massive particles, WIMPs and axions, but none have been directly detected. Experiments worldwide attempt to capture these elusive particles through detectors placed deep underground or by trying to create them in particle accelerators, yet the mystery persists. Dark energy, accounting for about 70% of the universe's total energy content, is even more mysterious. It is thought to be responsible for the accelerated expansion of the universe, a discovery that came as a surprise to scientists in the late 1990s. Unlike dark matter, dark energy does not cluster in the same way it is uniformly spread throughout the universe and has a repulsive effect, pushing galaxies apart. This repulsive force is contrary to the attractive force of gravity, and understanding how it works is crucial for unraveling the fate of the universe. The precise nature of dark energy is a topic of intense debate and research. It is often associated with the cosmological constant, a term Einstein originally introduced in his equations of general relativity, then later called his biggest blunder. The cosmological constant represents a density of energy that fills space. But whether dark energy is truly constant or changes over time is still under investigation. Some theories suggest it could be a form of vacuum energy, while others propose it might be due to a new field or force unknown to current physics. Together, dark matter and dark energy form the foundation of the cosmic web, shaping the universe's structure and driving its expansion. The question of whether there are other universes beyond our own opens a captivating chapter in the story of cosmology, filled with the potential for infinite possibilities and the allure of the unknown. This concept, often referred to as the multiverse theory, suggests that our universe might be just one of countless others, each with its own laws of physics, constants, and structures. The multiverse theory. The multiverse theory is not just a product of science fiction, but has emerged from theoretical physics and cosmology as a serious proposition attempting to address some of the most perplexing questions about the nature of existence and reality. One pathway leading to the multiverse theory is the framework of cosmic inflation. Cosmic inflation proposes that the universe underwent a period of exponential expansion immediately after the Big Bang, smoothing out and homogenizing the observable universe. However, some theories of inflation suggest that this process could be eternal, happening in different regions at different times, leading to the creation of multiple, causally disconnected regions or bubble universes, each potentially harboring its own version of physics. This model of the multiverse emerges naturally from the mathematics of inflation, presenting a cosmos where our universe is but a bubble in a frothy sea of universe bubbles. String theory, a candidate for the theory of everything attempting to reconcile quantum mechanics with general relativity, also lends itself to the idea of a multiverse. In string theory, the fundamental constituents of reality are not point particles but tiny, vibrating strings. The way these strings vibrate determines the nature of particles and forces in the universe. String theory allows for a vast landscape of possible solutions, each corresponding to a different set of physical laws and constants, implying a vast multiverse where each solution represents a different universe. The multiverse theory also offers a potential explanation for the fine-tuning of the physical constants in our universe. Some physical constants, like the strength of the gravitational force or the mass of the electron, seem to be finely tuned for the emergence of life. One explanation offered by the multiverse theory is that with a vast number of universes, each with different physical laws and constants, it is not surprising that at least one our own has the right conditions for life. This statistical argument, known as the anthropic principle, suggests that we observe these conditions simply because we are here to observe them. Despite the compelling nature of the multiverse theory, it remains highly speculative and controversial, primarily due to the significant challenge in testing it empirically. The very nature of the multiverse, separate universes causally disconnected from our own places, it beyond the reach of direct observation or experimentation. As such, the theory straddles the fine line between physics and philosophy, offering tantalizing solutions to fundamental problems while challenging our ability to provide empirical evidence. The role of gravity. The weakest yet most pervasive of the fundamental forces is the master sculptor of the universe, shaping the cosmos on every scale, from the smallest particles to the vast expanses between galaxies. This force, described by Einstein's general theory of relativity as the curvature of space-time caused by mass and energy, dictates the cosmic ballet of celestial bodies and the universe's evolution. At the heart of gravity's influence is its role in the formation of structures in the universe. After the Big Bang, the universe was a nearly uniform hot soup of particles. As it expanded and cooled, slight variations in density, magnified by the gravitational pull of denser regions, led to the accumulation of gas and dust into the first stars and galaxies. These initial structures acted as gravitational wells, pulling in more material and merging with other structures to form the vast web of galaxies we observe today. Gravity's reach extends beyond the formation of galaxies, influencing their behavior and interaction. Galaxies can be drawn together into groups and clusters by their mutual gravitational attraction, forming intricate networks connected by filaments of dark matter. This dark matter, constituting about 85% of the universe's total matter, exerts gravitational forces that shape the large-scale structure of the universe, even though it does not interact with light and remains invisible to our direct observation. The dance of galaxies under gravity-esque guidance can lead to dramatic events. Galaxies can collide and merge, driven entirely by gravitational attraction. These cosmic collisions are not destructive but transformative, leading to the birth of new stars as gas clouds within colliding galaxies compress and ignite. Our Milky Way galaxy is on a collision course with the Andromeda Galaxy, with their eventual merger expected in about 4 billion years, a testament to the relentless pull of gravity. On a grander scale, gravity is responsible for the overall dynamics of the universe. It competes with dark energy, a mysterious force driving the accelerated expansion of the universe. While gravity seeks to pull structures together, dark energy pushes them apart. The balance between these forces determines the cosmos' fate, whether it will continue to expand indefinitely, slow down, or eventually collapse back on itself in a big crunch. Gravity also plays a crucial role in the life cycles of stars. It compacts gas and dust to form stars and later drives their evolution and demise. In the cores of stars, gravity creates the intense pressure and heat necessary for nuclear fusion, the process that powers stars and produces the heavier elements essential for life. When a star exhausts its nuclear fuel, gravity can lead to its collapse, resulting in a supernova explosion or forming a neutron star or black hole, objects so dense that not even light can escape their gravitational grip. In the realm of planets and their orbits, gravity again takes center stage. It keeps planets orbiting stars, moons around planets, and dictates the trajectories of comets and asteroids. The tides on Earth, caused by the gravitational pull of the Moon and to a lesser extent the Sun, are daily reminders of gravity's influence on our world. Gravitational lensing is a remarkable phenomenon that serves as a cosmic magnifying glass, bending the path of light around massive objects like galaxies or clusters of galaxies, allowing us to observe distant parts of the universe that would otherwise be hidden from view. This effect, predicted by Einstein's theory of general relativity, occurs when the massive body-esque gravitational field distorts the fabric of space-time, bending the light from more distant objects around it. The result is much like that of an optical lens, magnifying, distorting, and sometimes even multiplying the image of the object behind it. The beauty of gravitational lensing lies in its ability to provide astronomers with a powerful tool for observing the universe. It can magnify distant galaxies so far away their light is faint, and would not be detectable with current telescopes without the boost provided by lensing. This allows scientists to study these galaxies' properties, including their structure, star formation rate, and overall composition, providing valuable insights into the early universe. Gravitational lensing can reveal the presence of dark matter. Since dark matter does not emit, absorb, or reflect light, it is invisible to direct observation. However, its mass contributes to gravitational lensing, affecting the degree to which light is bent. By analyzing the lensing effect, astronomers can map the distribution of dark matter around galaxies and clusters, offering clues about its nature and role in the universe's structure and evolution. Gravitational lensing is classified into 3 main categories based on the observed effect: strong lensing, weak lensing, and microlensing. Strong lensing creates highly visible distortions, such as Einstein rings, arcs, and multiple images of the same galaxy. Weak lensing, while more subtle, affects the shapes of background galaxies on a larger scale, slightly distorting their appearance in a way that can be statistically measured to infer the distribution of mass in the foreground structure. Microlensing occurs when a single star passes in front of another, causing a temporary increase in brightness that can reveal objects otherwise too dim to see. One of the most exciting applications of gravitational lensing is the search for exoplanets and studying dark energy. By observing how light from distant stars is bent by an intervening object's gravitational field, astronomers can detect planets orbiting stars in our galaxy. Similarly, studying how the mass distribution in the universe has evolved through lensing can gain insights into dark energy's nature and its effect on the universe's expansion. Black holes. Black holes, the universe's most mysterious objects, are regions in space where gravity is so strong that nothing, not even light, can escape from them. The formation and evolution of black holes are fascinating processes that stretch our understanding of physics to its limits. Black holes can form in several ways, but the most common method is through the collapse of massive stars. When a star much more massive than our Sun exhausts its nuclear fuel, it can no longer produce the energy needed to counteract the gravitational force trying to compress it. The star's core collapses under its gravity, and if the star is sufficiently massive, this collapse will continue until it forms a singularity, a point of infinite density, where the laws of physics as we know them break down. The boundary surrounding this point, beyond which nothing can escape, is known as the event horizon. It is the point of no return for matter or light and marks the birth of a black hole. The size of a black hole is directly related to its mass. The more mass that collapses into the singularity, the larger the event horizon, and consequently, the larger the black hole. Stellar black holes formed from the collapse of individual stars are among the most common types. However, black holes can also grow by accreting matter from their surroundings or merging with other black holes. This accretion of mass can lead to the formation of supermassive black holes, residing at the centers of most galaxies, including our Milky Way. These giants can have masses millions to billions of times that of our Sun. The evolution of black holes over time is a subject of intense study. As black holes accrete matter, they can emit powerful jets of particles and radiation, a process not fully understood but thought to involve the magnetic fields of the accreted material and the black hole's rotation. This emission can influence the black hole's surroundings, affecting star formation and galaxy evolution. Black holes can also evaporate over time through a process known as Hawking radiation, named after physicist Stephen Hawking, who proposed it. According to this theory, black holes are not completely black, but emit small amounts of thermal radiation due to quantum effects near the event horizon. This radiation causes the black hole to lose mass and, over very long timescales, could lead to its complete evaporation. However, for most black holes, this process is exceedingly slow compared to the cosmic timescales over which they accrete mass, making it a minor effect in their overall evolution. Life in the universe. The conditions necessary for life as we know it are a blend of chemical, physical, and environmental factors that converge in a delicate balance, enabling the emergence and sustenance of biological organisms. Central to our understanding of these conditions is the concept of the habitable zone, also known as the Goldilocks zone, a region around a star where temperatures are just right for liquid water to exist on a planet's surface. Water is the lifeblood of biological processes on Earth, serving as a solvent in which biochemical reactions essential for life occur. Beyond the presence of liquid water, life requires a suitable atmosphere for several reasons. An atmosphere can offer protection from harmful cosmic and solar radiation, help retain heat to maintain a stable temperature range, and contain the gases critical for life processes. For example, on Earth, oxygen is vital for most forms of life, while carbon dioxide plays a crucial role in photosynthesis, a process that underpins the food chain. Chemical elements are also foundational to life. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are considered the building blocks of life, making up nucleic acids, proteins, carbohydrates, and lipids. These elements combine in various ways to form the complex molecules necessary for life. The ability of carbon to form stable, long chains makes it uniquely suited as the backbone of organic molecules. The source of energy is another critical condition for life. On Earth, life primarily derives its energy from the sun, with plants capturing sunlight through photosynthesis and converting it into usable energy. However, discovering life forms in extreme environments on Earth, such as near hydrothermal vents on the ocean floor, has expanded our understanding of possible energy sources for life. These organisms rely on chemosynthesis, using chemical reactions to derive energy, suggesting that life could exist in environments without sunlight, provided there is a suitable energy source. Stability of environmental conditions over time is essential for the development of complex life forms. Sudden changes in temperature, atmospheric composition, or radiation levels can disrupt life processes. Planets with stable orbits and protective magnetic fields are more likely to maintain the consistent conditions necessary for life. The quest to understand the conditions necessary for life extends beyond our solar system to exoplanets orbiting other stars. Scientists search for exoplanets in their star's habitable zone and with characteristics indicating liquid water, a suitable atmosphere, and potential life-sustaining chemistry. Discovering such planets excites the imagination and fuels scientific inquiry, pushing the boundaries of our search for life beyond Earth. Life in the Milky Way. The question of whether there is life elsewhere in the Milky Way is profound, blending the realms of science, philosophy, and even fiction. Despite extensive research and exploration, definitive evidence of extraterrestrial life within our galaxy remains elusive. However, the scientific pursuit to answer this question has yielded fascinating insights and increased the possibility that we are not alone. Our Milky Way galaxy is home to hundreds of billions of stars, many likely to have planets orbiting them. Discovering these exoplanets, particularly those in their star's habitable zone, where conditions might allow liquid water, has significantly expanded our search for life. Thousands of these exoplanets have been identified, and among them, a number have characteristics suggesting they could potentially harbor life. The criteria for habitability extend beyond just being in the habitable zone. Factors such as the planet's atmosphere, magnetic field, and geological activity play crucial roles in determining its potential to support life. An atmosphere can protect life forms from harmful cosmic rays and provide essential gases for biological processes, while geological activity can recycle vital elements and support a stable climate. Astrobiology, the study of the origin, evolution, distribution, and future of life in the universe, employs a multidisciplinary approach to investigate these possibilities. Scientists use a combination of astronomy, biology, geology, and chemistry to understand the conditions under which life can arise and persist. This includes studying extreme environments on Earth, such as deep-sea vents and arid deserts, where life exists in conditions previously thought inhospitable. These studies help refine our understanding of the potential for life to exist in extreme conditions elsewhere in the galaxy. One of the most promising tools in the search for extraterrestrial life is the analysis of exoplanets' atmospheric compositions. By studying the light from a star as it passes through a planet's atmosphere, scientists can detect the presence of gases like oxygen and methane closely linked to biological activity on Earth. Future telescopes and missions are being designed to carry out these detailed observations, bringing us closer to identifying signs of life. The search for extraterrestrial life also includes searching for microbial life within our solar system. Missions to Mars, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, aim to explore environments where life might exist or might have existed. These environments include subsurface oceans on Europa and Enceladus, and the ancient river valleys and lake beds on Mars. While the search for life elsewhere in the Milky Way is ongoing, it is clear that the galaxy is filled with many planets and moons, many of which may offer the conditions necessary for life to emerge and evolve. The absence of evidence is not evidence of absence, and as our technologies advance and our understanding deepens, the possibility of discovering life beyond Earth remains an open and tantalizing question: the search for extraterrestrial life. The search for extraterrestrial life is an exhilarating journey stretching the boundaries of our knowledge and technology, exploring the vastness of space to answer one of humanity's oldest questions: are we alone in the universe? This quest employs various methods to uncover signs of life beyond Earth, ranging from the microscopic to intelligent civilizations. One primary method is the study of exoplanets, planets orbiting stars outside our solar system. Astronomers use telescopes equipped with sophisticated instruments to detect these distant worlds indirectly by observing their effects on their host stars. The transit method watches for the slight dimming of a star's light as a planet passes in front of it, while the radial velocity method measures the star's slight wobble caused by the gravitational pull of orbiting planets. These observations reveal the presence of exoplanets and essential characteristics such as their size, orbit, and critically, their position relative to their star's habitable zone. Technological advancements now allow scientists to push the search further, analyzing the atmospheres of exoplanets for chemical signatures that might indicate the presence of life. By examining the light that passes through a planet's atmosphere, researchers can identify the fingerprints of specific molecules such as oxygen, methane, and water vapor closely associated with biological activity on Earth. Future missions aim to refine these techniques, offering the potential to detect more subtle indicators of life. Another avenue in the search for extraterrestrial life is the direct exploration of bodies within our solar system. Robotic missions to Mars, for example, have sought evidence of past or present microbial life by analyzing the planet's soil and atmosphere. The search extends to the icy moons of Jupiter and Saturn, such as Europa and Enceladus, where subsurface oceans beneath their frozen crusts could provide habitable conditions for life. These missions collect data on these moons' composition, geology, and potential hydrothermal activity, seeking environments where life might exist. The search for intelligent life forms, known as the Search for Extraterrestrial Intelligence SETI, takes a different approach, scanning the cosmos for signals that could only be produced by advanced technologies. Using radio and optical telescopes, SETI researchers listen for deliberate signals or look for evidence of megastructures that alter the light of their host stars in detectable ways. Although no definitive signs of intelligent life have been detected, the search continues, expanding to new wavelengths and more sensitive instruments. In addition to these targeted searches, scientists also explore the possibility of detecting life through the study of meteorites and the interstellar medium. Some meteorites found on Earth, believed to have originated from Mars, contain complex organic molecules, raising questions about the potential for life elsewhere in the solar system. Similarly, detecting complex organic molecules in the clouds of gas and dust between stars suggests that the building blocks of life might be more common in the universe than previously thought. The cosmic web. The cosmic web is a vast, intricate structure forming the backbone of the universe, comprising galaxies, galaxy clusters, and intergalactic gas, all interconnected by filaments of dark matter. This immense network, spanning billions of light-years, reveals the universe's large-scale structure, resembling a web with dense nodes of galaxies connected by filaments, surrounding vast, empty voids. This cosmic architecture results from the gravitational pull of dark matter, an invisible substance making up about 85% of the universe's total matter content. Although dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes, its presence and distribution can be inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters, and gravitational lensing, where the path of light from distant galaxies is bent by the gravitational field of dark matter. The formation of the cosmic web began shortly after the Big Bang, during the era of cosmic inflation, when the universe expanded exponentially in a fraction of a second. Tiny quantum fluctuations were stretched to macroscopic scales, creating slight variations in the density of matter across the universe. As the universe continued to expand and cool, gravity began to amplify these initial irregularities, pulling matter into denser regions and leaving behind voids. Over billions of years, this process led to the formation of the cosmic web's filamentary structure, with dark matter acting as the scaffold on which visible matter congregated and formed stars, galaxies, and galaxy clusters. Observations of the cosmic microwave background CMB, the afterglow of the Big Bang, provide a snapshot of the universe approximately 380,000 years after its inception, showing the earliest seeds of the cosmic web. These tiny fluctuations in the CMB's temperature correspond to regions of slightly higher and lower density, the precursors to the cosmic web's filaments and voids. The cosmic web's filaments are not only made of dark matter, but also contain intergalactic gas and dust, the raw materials for star and galaxy formation. These filaments can span hundreds of millions of light years and are the sites where galaxies are born and evolve, drawn together by gravity. Where filaments intersect, the density of matter is highest, leading to the formation of galaxy clusters and superclusters, the most massive structures in the universe. Studying the cosmic web is crucial for understanding the universe's evolution, dark matter distribution and behavior, and galaxy formation and evolution processes. Astronomers use various observational techniques, including large-scale galaxy surveys and simulations, to map the cosmic web and probe its properties. These studies shed light on the universe's large-scale structure and help constrain cosmological models, offering insights into dark matter, dark energy, and the overall dynamics of the cosmos. Influence of the cosmic web on galaxies. The cosmic web, with its vast network of dark matter filaments crisscrossing the universe, plays a pivotal role in the formation and evolution of galaxies, acting as the cosmic framework within which galaxies are born and grow. This immense structure dictates not only where galaxies form, but also influences their properties and the pace at which they evolve. At the heart of galaxy formation within the cosmic web is dark matter. Though invisible and detectable only through its gravitational effects, dark matter constitutes the majority of the universe's matter. It forms the skeleton of the cosmic web, with its dense regions attracting baryonic matter, normal matter that makes up stars, planets, and living organisms through gravity. In the early universe, shortly after the Big Bang, matter was nearly uniformly distributed. However, slight overdensities, magnified by the gravitational pull of dark matter, began to attract surrounding matter. These overdensities are the seeds from which the cosmic web and subsequently galaxies grew. Dark matter's gravitational attraction caused gas and dust to accumulate in the denser regions of the web, forming the first galaxies in areas where dark matter filaments intersected, creating deep gravitational wells. The cosmic web's filaments act like cosmic highways, channeling gas and dust into these intersections, or nodes, where galaxy clusters and superclusters form. This process is dynamic and ongoing, with galaxies continuing to accrete matter from their surroundings, leading to new star formation and galaxy growth over time. The cosmic web's structure influences how galaxies interact and merge. Galaxies within the same filament are drawn toward common gravitational centers, leading to interactions and mergers fundamental to galaxy evolution. These mergers can trigger bursts of star formation, leading to the rapid growth of galaxies and forming elliptical galaxies from the merger of spiral galaxies. The cosmic web's distribution of galaxies also affects their properties. For instance, galaxies in denser regions of the web, such as galaxy clusters, tend to be older, redder, and more elliptical, having exhausted their gas reserves and ceased forming new stars. In contrast, galaxies in the less dense regions, or the filaments themselves, are typically younger, bluer, and still forming stars. Galaxy formation within the cosmic web is also influenced by feedback processes. For example, supernova explosions and active galactic nuclei can inject energy into the surrounding medium, heating it and preventing the further collapse of gas into stars. This feedback can regulate star formation within galaxies and influence the cosmic web's evolution over cosmic time. Evidence for the cosmic web. The existence of the cosmic web, a vast network of interconnected filaments of dark matter governing the distribution of galaxies and galaxy clusters across the universe, is supported by observational evidence and theoretical predictions. This evidence comes from various sources, painting a picture of the universe's large-scale structure that matches the predictions made by cosmic evolution models. One of the primary pieces of evidence for the cosmic web comes from mapping galaxies and galaxy clusters. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey (SDSS), have cataloged millions of galaxies, revealing a pattern that matches the filamentary structure predicted by the cosmic web. These surveys show galaxies are not randomly distributed, but clustered along filaments, surrounding vast voids where few galaxies are found. The distribution and motion of galaxies within these structures are influenced by the underlying dark matter, which, although invisible, exerts gravitational forces shaping the web's architecture. Gravitational lensing also offers compelling evidence for the cosmic web. This phenomenon occurs when the gravity of a massive object, such as a galaxy cluster, bends the light from more distant galaxies, acting like a lens that magnifies and distorts the background light. Observations of gravitational lensing not only confirm the presence of massive structures along the lines of sight, but also map the distribution of dark matter within these structures. The lensing patterns observed are consistent with a universe filled with filaments of dark matter, as predicted by the cosmic web model. Cosmological simulations provide additional support for the cosmic web's existence. These simulations use supercomputers to model the universe's evolution from shortly after the Big Bang to the present day, based on the laws of physics and initial conditions derived from CMB observations. The results of these simulations, which show the gradual formation of a web-like structure of dark matter filaments and voids, closely match the distribution of galaxies and dark matter inferred from observations. Studies of the intergalactic medium IgM, the diffuse gas filling the space between galaxies, have detected the presence of filaments through absorption lines in the spectra of distant quasars. These lines, caused by gas in the IgM absorbing light at specific wavelengths, indicate the presence of hydrogen gas in structures corresponding to the cosmic web's predicted filaments. The expansion of the universe. The universe's expansion is not akin to galaxies moving through space away from a central point, but rather space itself expanding, carrying galaxies along with it. Imagine the universe as a balloon with dots representing galaxies. As the balloon inflates, the dots move away from each other. This analogy helps visualize how galaxies can move apart without implying a central point from which everything is retreating. One of the key pieces of evidence for the universe's expansion comes from observing the cosmic microwave background CMB radiation, a faint glow left over from the Big Bang. The uniformity and distribution of the CMB across the sky support the theory that the universe has been expanding from a hot, dense state to its current cooler, more spread-out condition. The rate of this expansion is quantified by the Hubble constant, measuring the velocity at which galaxies recede from us per unit distance. However, precise measurements of the Hubble constant have revealed a tension between the value obtained from observations of the early universe, such as the CMB, and the value derived from observations of the local universe, such as supernovae in nearby galaxies. This discrepancy suggests that our understanding of the cosmos might be incomplete, hinting at new physics or refining existing models. Moreover, the universe's expansion is not only continuing but accelerating, a discovery made in the late 1990s through observations of distant supernovae. This acceleration is attributed to dark energy, a mysterious force permeating all space and exerting a repulsive effect, counteracting gravity. While the exact nature of dark energy remains one of the biggest questions in cosmology, it is thought to constitute about 70% of the universe's total energy content. The ongoing expansion and acceleration of the universe have profound implications for its fate. If dark energy continues to dominate, the universe could expand forever, becoming colder and emptier over time, a scenario known as the Big Freeze. Alternatively, if dark energy's properties change, it could lead to different outcomes, such as the Big Crunch, where the universe collapses back on itself, or the Big Rip, where galaxies, stars, and even atoms are torn apart by the accelerating expansion. Influence of expansion on galaxies. The universe's expansion, a fundamental concept shaping our understanding of cosmology, significantly impacts galaxies and their evolution. This process, driven by the mysterious force of dark energy, influences galaxies in several profound ways, affecting their formation, interaction, and ultimate destiny in the cosmos. At the largest scales, the universe's expansion means that galaxies are moving away from each other. This observation, first made by Edwin Hubble in the 1920s, is often described by the analogy of raisins in a rising loaf of bread. As the bread expands, the raisins' galaxies move further apart. This expansion is uniform, meaning that on average, every galaxy sees every other galaxy moving away from it, with more distant galaxies receding faster, a relationship described by Hubble's law. However, the universe's expansion does not mean all galaxies are continually getting farther apart. Within local groups or clusters of galaxies, such as our local group, gravitational attraction is strong enough to hold galaxies together despite the overall expansion. Our Milky Way, for instance, is gravitationally bound to the Andromeda Galaxy, and they are on a collision course, expected to merge in about 4 billion years. Thus, while the universe expands, local clusters of galaxies can still come together, merge, and form larger structures. The universe's expansion influences galaxies' formation by stretching the fabric of space, affecting the distribution of dark and baryonic matter, the matter making up stars, planets, and life. Dark matter, which does not interact with light but exerts gravitational force, forms the cosmic web as structure, filaments and halos that attract baryonic matter. As the universe expands, the growth of these structures follows, guiding the formation of galaxies along the dense regions of dark matter. The universe's expansion also affects light traveling through it, a phenomenon known as redshift. As light from distant galaxies travels toward us, the expansion of space stretches the wavelengths of this light, shifting them toward the red end of the spectrum. This redshift helps astronomers measure the universe's expansion rate and provides clues about galaxies' age and distance, allowing us to peer back in time and observe galaxies in their infancy shortly after the Big Bang. The future impact of the universe's expansion on galaxies depends on dark energy's nature. If the expansion continues to accelerate, as current observations suggest, distant galaxies will eventually recede from view, their light stretched to wavelengths too long to detect, and the universe will become much lonelier, with galaxies isolated in their local groups amidst an ever-expanding void. The influence of magnetic fields. Magnetic fields, though invisible to the naked eye, play a pivotal role in shaping the cosmos, influencing various astrophysical processes and structures across the universe. These fields are not isolated phenomena, but interwoven into the cosmos' fabric, from the smallest scales of planets and stars to the vast expanses between galaxies. Within stars, including our Sun, magnetic fields are generated through dynamo action, where the convective movement of electrically conducting fluids, such as plasma, generates magnetic energy. These magnetic fields can lead to phenomena such as sunspots on the Sun's surface and the spectacular eruptions known as solar flares and coronal mass ejections. Such events can directly impact Earth, affecting satellite communications, power grids, and creating the natural light displays known as auroras. On a larger scale, magnetic fields play a crucial role in stars' life cycles. In the cold, dense gas and dust clouds where stars are born, magnetic fields can influence the collapse of these clouds, affecting the formation rate and initial mass distribution of new stars. The fields can also direct the flow of gas and dust in protostellar disks, shaping planets' formation. Magnetic fields are integral to the dynamics of the interstellar medium ISM, the gas and dust filling the space between stars in a galaxy. They contribute to the support of these clouds against gravitational collapse, help regulate star formation, and channel the flow of charged particles throughout the galaxy. The interaction between magnetic fields and the ISM is a key factor in the evolution of galaxies, influencing their structure and the distribution of matter within them. Magnetic fields play significant roles in galaxies and intergalactic space. They can be found within galaxy clusters, the largest gravitationally bound structures in the universe, where they are thought to be amplified by the turbulent motion of the intra-cluster medium. These fields can extend over millions of light years and impact the propagation of cosmic rays, charged particles traveling through the universe at nearly the speed of light. The origin of cosmic magnetic fields, particularly those permeating intergalactic space, remains one of astrophysics' great mysteries. It is theorized that they could have been seeded in the early universe and amplified over time through various dynamical processes. Understanding these primordial fields could provide insights into the early universe's conditions and cosmic evolution's nature. Despite their ubiquity and importance, magnetic fields in the universe are challenging to study directly. Astronomers rely on indirect methods, such as studying the polarization of light or the behavior of charged particles, to map and measure these fields. Advances in observational techniques and theoretical models continue to shed light on magnetic fields' role in the cosmos, revealing a complex and dynamic universe shaped by these unseen forces. Influence of magnetic fields on star and galaxy formation. Magnetic fields play a nuanced and critical role in star and galaxy formation, acting as an invisible scaffold that influences the behavior of cosmic gas and dust. These fields are not merely passive participants, but active elements shaping the universe's structure and dynamics. In star formation, magnetic fields exert a significant influence from the initial stages. Gas and dust clouds in galaxies, known as molecular clouds, are the birthplaces of stars. Within these clouds, magnetic fields interact with the gas-s charged particles, influencing the cloud-s collapse under gravity. These fields can provide support against gravitational collapse in certain directions, leading to the cloud-s elongation and potentially